Look up at the night sky on a clear, dark evening. You see countless stars, the soft glow of our own Milky Way stretching across the heavens, a scene of profound, silent beauty. But now, I want you to picture something that challenges that very serenity. Imagine a single point of light, so unimaginably fierce and brilliant that it outshines not just one star, but every single star in an entire galaxy combined. This isn't science fiction. This is a quasar, one of the most violent and energetic objects in the entire cosmos, and it represents just the tip of a truly bizarre astronomical iceberg we call an active galactic nucleus. For decades, these cosmic powerhouses have defied easy explanation, pushing the boundaries of our understanding and forcing us to rethink the fundamental laws of physics on a scale that is almost impossible to comprehend. What you are about to witness is a journey to the very edge of known reality, a deep dive into the heart of cosmic monsters that dwarf anything in our own galactic neighborhood. We are going to explore the 25 most peculiar, mind-bending, and utterly bizarre phenomena associated with quasars and their active galactic nuclei. This is a story of supermassive black holes, some weighing in at billions of times the mass of our Sun, and the chaotic, luminous maelstroms of gas and dust that swirl into them, releasing more energy in a single second than our Sun will over its entire multi-billion-year lifetime. The sheer scale of power involved is both terrifying and beautiful, a testament to the universe's capacity for extremes that challenge our very perception of what is possible. So prepare to have your concept of reality stretched. We will uncover jets of matter shooting across millions of light years at nearly the speed of light, witness time itself behaving strangely in the grip of immense gravity, and question whether these brilliant beacons from the early universe hold the key to understanding the fate of all galaxies, including our own. This exploration is more than just a list of facts. It is an invitation to share in the wonder and the mystery that drives astronomers to peer ever deeper into the void, seeking answers to questions we are only just learning how to ask. Let's begin our countdown of the 25 most bizarre phenomena of quasars and active galactic nuclei. And it all begins with a concept that sounds like something straight out of a cosmic horror story, yet it is the very heart of every single active galaxy. Our first bizarre phenomenon is the supermassive black hole engine. Picture the most efficient and terrifying power plant imaginable, buried in the center of a distant galaxy. This isn't fueled by coal or nuclear fusion. Its fuel is entire stars, vast clouds of gas, and anything else that wanders too close. At the core of every quasar and active galactic nucleus lies a supermassive black hole, a gravitational singularity with a mass that can be millions, even billions of times greater than our Sun. But a black hole itself doesn't emit light. It's the definition of darkness. So how does this cosmic vacuum cleaner become the universe's most brilliant beacon? The answer lies in a frenzied, chaotic process known as accretion. Before matter vanishes forever across the black hole's event horizon, the point of no return, it gets caught in an immense, swirling whirlpool called an accretion disk. Imagine a drain at the center of a galaxy, with water spiraling inward at fantastic speeds. But this is no ordinary drain. The forces at play are so immense that the gas and dust in this disk are compressed and heated through friction and gravitational stresses to temperatures of millions of degrees. This superheated material doesn't just get warm. It becomes a ferocious plasma, glowing with an intense light across the entire electromagnetic spectrum, from radio waves to X-rays. This is the primary source of the quasar's blinding brilliance. The conversion of gravitational energy into light within this disk is so extraordinarily efficient that it can far outpace the collective light of every star in its host galaxy. We are talking about an object that can outshine 1 trillion suns, all emanating from a region of space not much larger than our own solar system. The sheer power output is almost beyond human comprehension. To put it in perspective, a typical quasar releases more energy every single second than our Sun will over its entire 10 billion-year lifespan. This means the light you see from a quasar, which may have traveled for billions of years to reach your telescope, was generated in a continuous, unimaginable cosmic explosion happening in a remarkably small volume of space. It's the ultimate demonstration of power through destruction, where the black hole's immense gravity rips matter apart, and in its final death spiral, that matter screams across the universe in a final, glorious flash of light. This engine is the fundamental reason these objects were so baffling when first discovered, a single point of light that defied all logic, outshining entire galaxies from the very edge of the observable universe. Now, if the supermassive black hole engine represents the heart of this cosmic beast, then the relativistic jets are its roaring breath, a pair of focused, unimaginably powerful beams that scream into the intergalactic void. We just left matter swirling into the accretion disk, but not all of that superheated plasma is destined to fall in. In one of the most spectacular escapes in the universe, a fraction of this material gets channeled and launched away from the black hole, perpendicular to the disk, at velocities so close to the speed of light that the laws of relativity are pushed to their absolute limit. These are not gentle, diffuse winds. They are exquisitely narrow and focused beams of energy and matter, functioning like cosmic blowtorches that can stretch for distances that defy human comprehension. Some of these jets have been observed extending for over 1 million light-years, meaning the beam you see originating at the galaxy's center is longer than the entire Milky Way galaxy is wide. We are looking at structures so vast they connect galaxies to the emptiness between them. The formation of these jets remains one of the most active and challenging areas of astrophysical research, but the prevailing theory involves a complex and violent interplay between the black hole's rotation and its immensely powerful magnetic fields. As the black hole spins, it drags the very fabric of spacetime around with it, an effect known as frame dragging. This rotation, combined with the twisted, dynamo-like motion of the accretion disk, can wind up magnetic field lines like immensely powerful cosmic coils. Think of it as a natural particle accelerator on a scale we could never hope to build on Earth. These magnetic fields become so concentrated and energetic that they can funnel some of the infalling material outward, accelerating it along the black hole's spin axis. The process is akin to tightening the nozzle on a garden hose to create a powerful, long-range stream. But here the nozzle is made of fundamental forces governing the universe, and the water is a searing plasma traveling at 99.9% the speed of light. What makes these jets truly bizarre beyond their sheer scale and speed is their incredible stability and focus over such astronomical distances. How does a beam of plasma remain so tightly collimated as it travels for millions of years? The answer again lies in those magnetic fields, which act like a containing sheath, preventing the jet from dispersing and dissipating into the thin intergalactic medium. When these relativistic jets slam into the tenuous gas that exists between galaxies, they create immense luminous structures known as radio lobes, which can glow brightly at radio wavelengths for eons after the central engine has quieted down. In some cases, the impact is so violent that it can trigger or suppress star formation in entire galactic neighborhoods, demonstrating that the influence of a single active galactic nucleus can reach far beyond its own home. We are witnessing a feedback mechanism of almost godlike power, where the death cry of matter falling into a black hole can, paradoxically, give birth to new structures and influence the evolution of the cosmos on the very largest scales. But if you thought the scale of these relativistic jets was difficult to grasp, the next phenomenon will truly bend your mind, because it reveals a secret hidden in the flickering light of these cosmic beacons. We come to the mind-boggling variability of quasars, Imagine watching a star in the sky, and over the course of a single night, you see it double in brightness, then fade back down. For ordinary stars, this is impossible. Their light is stable over human timescales. Yet for many quasars and other active galactic nuclei, this isn't just possible, it's routine. Astronomers have observed these objects undergo significant changes in their luminosity over periods as short as hours or days. This isn't a slow, gradual brightening over millions of years. This is a rapid, dramatic flicker, as if someone were fiddling with a cosmic dimmer switch on an object that outshines entire galaxies. This rapid variability isn't just a curious observation. It is one of the most powerful diagnostic tools we have for understanding the true nature of these objects. The key lies in a fundamental principle of physics. No signal, not even light itself, can travel faster than the speed of light. This universal speed limit places a strict constraint on the maximum possible size of any object that changes its brightness quickly. Think of it this way: if an object is 1 light year across and the entire thing brightens at once, it would take a full year for the light from the far side to reach us and contribute to that brightening signal. The change would appear smooth and slow from our perspective, but if we see the entire object double in brightness in just 1 day, that tells us the region responsible for the outburst cannot be much larger than 1 light day across. The entire emitting region must be causally connected. The news of the brightening has to be able to travel across the source within the time we see the change happen. When we apply this logic to a quasar that varies significantly over mere hours, we are forced to a staggering conclusion. The region producing this unimaginable energy, enough to outshine 1 trillion suns, must be compressed into a volume of space not much larger than our own solar system. To put that in perspective, the energy output of an entire galaxy, typically spread across tens of thousands of light years, is here being generated in a region so compact that light can cross it in a matter of hours. This is the ultimate cosmic contradiction. An object of almost incomprehensible power, rivaling the combined output of billions of stars, is confined to a space that is, on the cosmic scale, infinitesimally small. It's like trying to pack the entire explosive energy of a supernova into the volume of a teacup. The very idea challenges our most basic intuitions about physics and energy density. This incredible compactness was one of the key pieces of evidence that originally led astronomers to propose the supermassive black hole accretion disk model. Only the intense gravitational field of a black hole can provide the necessary forces to heat and compress matter into such a small, incredibly energetic region. The variability we see is thought to arise from instabilities and flares within the inner, hottest parts of the accretion disk, or from processes linked to the base of those relativistic jets. A sudden surge of material falling in, or a magnetic reconnection event similar to a solar flare but on a billion-fold more energetic scale, can cause a rapid brightening that then propagates through the compact region, allowing us to witness the entire event unfold in a shockingly short time. This flickering light, captured by our telescopes over countless nights, is our direct window into the heart of the maelstrom, giving us a real-time look at the violent and dynamic processes feeding the most powerful engines in the universe. Now, let's turn our attention from the rapid flickers of these brilliant engines to what their light can tell us about their place in the cosmos, because their incredible distance is itself one of the most profound and bizarre aspects of their nature. When quasars were first identified in the 1950s and 60s, they appeared as star-like points of light, but their spectra, the unique fingerprint of light that reveals their composition and velocity, were completely unlike anything seen from ordinary stars. They showed broad, powerful emission lines indicating vast clouds of hot, fast-moving gas, but the truly baffling part was that these familiar patterns of light were all dramatically shifted toward the red end of the electromagnetic spectrum. This phenomenon, known as redshift, was the key that unlocked their true identity as the most distant, and therefore the oldest permanently observable objects in the entire universe. Think of redshift like the cosmic version of the Doppler effect you experience with sound. When an ambulance speeds away from you, the sound waves are stretched, lowering the pitch of its siren. In exactly the same way, when a celestial object like a quasar is moving away from us at immense speed, the light waves it emits are stretched, shifting their color toward longer, redder wavelengths. For quasars, this redshift is not just significant, it is extreme. Some quasars have redshift so vast that their ultraviolet light, which is invisible to our eyes, has been stretched all the way into the infrared part of the spectrum by the time it travels across the cosmos to reach our telescopes. This tremendous redshift directly translates to distance and velocity, but not in the way you might initially think. It's not that these quasars are simply speeding through space on their own. Rather, they are being carried away from us by the expansion of the universe itself. The space between galaxies is literally stretching, and that stretching elongates the light waves traveling through it. The greater the redshift, the more space has expanded during the light's journey, and thus the farther away and the further back in time we are looking. This makes quasars the ultimate cosmic distance record holders. The most distant quasars we have observed are so far away that their light has been traveling for over 13 billion years to reach us. We are seeing them not as they are today, but as they were when the universe was less than 1 billion years old, a mere infant in cosmic terms. They are lighthouses from the dawn of time, their brilliant beams piercing the primordial darkness to give us a direct glimpse into an era when the first galaxies were still assembling themselves. This ability to look back in time is one of the most powerful tools in all of astronomy. By studying the light from these ancient quasars, we are effectively using the universe as a time machine. We can analyze the chemical elements present in the gas around them, witness the conditions that allowed supermassive black holes to grow to such staggering sizes so quickly after the Big Bang, and map the large-scale structure of the early cosmos. The sheer existence of these brilliant objects so early in the universe's history presents one of the most significant puzzles in modern astrophysics. How did supermassive black holes with masses of billions of suns have enough time to form and accumulate so much material in less than 1 billion years? Their presence in the young universe forces us to reconsider our models of how the first structures condensed and grew, suggesting that the seeds for these cosmic monsters were planted in the universe's very first moments, or that they grew through mechanisms we are only beginning to understand. Each new high redshift quasar discovered pushes the frontier of our observable universe a little further back, allowing us to test our theories against the most extreme conditions that ever existed. They are not just distant curiosities, they are fundamental probes of cosmology itself, helping us to measure the rate of the universe's expansion, understand the nature of dark energy, and ultimately trace our own cosmic lineage back to its spectacular and violent beginnings. Now, let's shift our focus from the quasars themselves to what happens on their epic journey across the cosmos, because their light becomes a tool for exploring the very fabric of the universe in one of the most beautiful and bizarre phenomena in all of astronomy, the Lyman alpha forest. When astronomers point their most powerful spectrographs at a distant quasar, they don't just see a clean, simple spectrum. Instead, they find something that looks like it's been meticulously combed over by the universe itself. The smooth continuum of light from the quasar is interrupted, not by 1 or 2 absorption lines, but by thousands, even tens of thousands of sharp, dark lines crowding together, creating a dense, intricate pattern that resembles the tangled branches of a forest. This is the Lyman alpha forest, and it represents a cosmic fossil record of unparalleled detail. The story of this forest begins with the simplest and most abundant element in the universe, hydrogen. In its neutral state, a hydrogen atom has a very specific appetite for light. It hungrily absorbs light at one particular wavelength in the far ultraviolet part of the spectrum, known as the Lyman alpha line. As the brilliant, pristine light from a distant quasar travels for billions of years to reach us, it passes through an immense cosmic landscape. It doesn't travel through pure emptiness. It voyages through the vast, filamentary structure of the cosmic web, a network of dark matter that is sparsely populated with clouds and filaments of primordial gas. Whenever this quasar light encounters a cloud of neutral hydrogen along its path, the atoms within that cloud act like tiny filters, plucking out that specific Lyman alpha wavelength from the beam of light. Each cloud imprints its own unique, dark fingerprint onto the quasar's spectrum. What makes this a forest, and not just a few trees, is the effect of cosmic expansion. Remember the redshift we discussed earlier? It doesn't just apply to the quasar itself. Every single hydrogen cloud between us and the quasar is also at a different distance, and therefore its absorption line is redshifted by a different amount. A cloud that is relatively close to us will have its Lyman alpha line shifted only a little into the ultraviolet. A cloud halfway to the quasar will have its line shifted further, perhaps into the visible blue part of the spectrum. And a cloud very close to the quasar will have its absorption line redshifted all the way into the red or even infrared. The result is that the single, specific Lyman alpha absorption line from countless individual clouds is smeared out across a huge range of wavelengths in the quasar spectrum. Instead of one dark line, we see a veritable thicket of them, each one representing a separate cloud of hydrogen at a unique distance, and therefore a unique look-back time in the history of the universe. This transforms a single quasar spectrum from a simple measurement into one of the most powerful probes of cosmic structure we possess. By meticulously cataloging every single absorption line in this forest, astronomers can effectively perform a core sample of the universe. It's as if the quasar's light is a brilliant surgical beam, and by studying the shadows cast upon it, we can map the distribution of otherwise invisible matter along a straight line that stretches billions of light years across space. This allows us to study the cosmic web directly, revealing how matter clumped and distributed itself over cosmic time. The density of the forest tells us about the amount of neutral hydrogen present at different epochs. The spacing and strength of the lines reveal the sizes and densities of these intergalactic clouds. We can even observe the forest change as we look at quasars at different distances. In the early universe, the forest is much denser, as more neutral hydrogen existed before it was ionized by the first stars and galaxies. The Lyman alpha forest is more than just a pretty pattern. It is a direct window into the universe's youth. It provides crucial evidence for the prevailing model of cosmology, confirming the large-scale structure predicted by supercomputer simulations of dark matter. These countless, wispy clouds are the building blocks of galaxies, the raw material that would eventually collapse to form the stars and planets we see today. By deciphering this unique barcode imprinted on the light of quasars, we are not just studying the most luminous objects in the cosmos. We are reading the autobiography of the universe itself, written in the subtle shadows of the most common substance there is. It is a humbling reminder that even the faintest traces, when viewed with enough precision, can reveal the grandest of designs. But this intricate cosmic barcode leads us to an even grander application of these brilliant beacons, one that pits them against the very fate of the universe. We now arrive at a phenomenon that could resolve one of the biggest tensions in modern cosmology, the quest to use quasars as standard candles. In astronomy, a standard candle is an object with a known intrinsic brightness. Think of it like a 100-watt light bulb. If you know a light bulb is always 100 watts, you can figure out how far away it is simply by measuring how dim it appears to you. The fainter it looks, the farther away it must be. For decades, astronomers have relied on certain types of stars, like Cepheid variables, and the cataclysmic explosions of white dwarfs known as Type Ia supernova, as their primary standard candles to measure the scale of the universe and the rate of its expansion. These tools were instrumental in the Nobel Prize-winning discovery that the universe's expansion is accelerating, driven by the mysterious force we call dark energy. The problem, however, is that there's a growing and significant discrepancy between measurements of the universe's expansion rate, known as the Hubble constant, when using different methods. It's a crisis in cosmology, suggesting we might be missing a fundamental piece of physics. This is where quasars enter the stage with a bold promise. Could these most luminous of objects, visible from the farthest reaches of space, serve as the next generation standard candle, allowing us to measure distances deeper into the cosmos than ever before and finally resolve this tension? The challenge has always been that quasars are notoriously messy and diverse. No two look exactly alike, their luminosities vary wildly, and they are anything but standard. They are like a collection of light bulbs with unknown and constantly flickering wattages. For a long time, the idea of using them as precise distance markers seemed like a fantasy. But a breakthrough came when astronomers noticed a surprising correlation buried deep within the chaotic light of certain quasars. It turns out that the very accretion disk we discussed earlier, the superheated whirlpool of matter around the black hole, emits light in a predictable way across different parts of the spectrum. Specifically, the disk glows brightly in the ultraviolet, and that same energetic environment also produces X-rays from a swirling corona of hot electrons, similar to the corona around our Sun, but infinitely more powerful. After studying thousands of quasars, researchers discovered a tight relationship between the amount of ultraviolet light a quasar produces and the amount of X-ray light it emits. It's as if, despite the vast differences in their overall brightness, all these quasars follow the same fundamental recipe for converting ultraviolet energy into X-ray energy. This correlation is the key that could unlock their potential as standard candles. Here's how it works in practice. By carefully measuring the observed X-ray brightness of a quasar, astronomers can use this known ultraviolet to X-ray relationship to calculate what its intrinsic ultraviolet brightness should be. They now have a theoretical 100-watt light bulb, so to speak. They then measure the actual, observed ultraviolet brightness from Earth. By comparing the intrinsic brightness to the observed dimmed brightness, they can calculate the distance the light has traveled, and thus the distance to the quasar itself. It's a beautiful piece of cosmic sleuthing, using one wavelength of light to predict another, and using the difference between prediction and observation to measure the vast emptiness of space. This method has a monumental advantage because quasars are so incredibly bright. We can apply this technique to objects that are vastly more distant than even the brightest supernova, probing the expansion history of the universe across an unprecedented 90% of cosmic time. Using quasars as standard candles is still a relatively new and refined technique, but the initial results are already shaking the foundations of cosmology. When astronomers construct the new cosmic distance ladder with quasars placed on its highest rungs, the measurements of the Hubble constant they derive are leaning toward one side of the great debate. They seem to align more closely with the value measured from the afterglow of the Big Bang, the cosmic microwave background, rather than the value obtained from local measurements using Cepheids and supernova. If this holds true, it could mean there is no error in our measurements, but rather that dark energy itself is not a constant force as we once thought. Perhaps it has evolved over the life of the universe, or maybe there is an entirely new particle or field influencing cosmic expansion that we have yet to discover. The humble quasar, once a mysterious and inexplicable point of light, may now hold the key to diagnosing the ultimate fate of everything, whether the universe will continue expanding forever in a silent, dark freeze, or if another, even more bizarre destiny awaits in the deep, dark future. But the journey of quasar light across the cosmos can take an even more twisted path than just passing through clouds of hydrogen. Sometimes the very fabric of space-time itself acts as a lens, warping and magnifying the light in a spectacular cosmic illusion known as gravitational lensing. This phenomenon takes the bizarre nature of quasars and amplifies it, quite literally, into one of the most visually striking and scientifically valuable events we can observe. The concept stems directly from Einstein's theory of general relativity, which tells us that mass warps the space around it. A massive object like a galaxy or a cluster of galaxies doesn't just pull on light with gravity, it actually curves the space through which the light is traveling. Think of it as placing a heavy bowling ball in the center of a stretched-out rubber sheet. If you then roll a marble past the bowling ball, its path will curve following the indentation. In the same way, when the light from a distant, brilliant quasar passes close to a massive foreground galaxy on its way to us, its path is bent. This cosmic bending of light can produce several astonishing effects. In the most dramatic and visually captivating cases, the foreground galaxy acts like a complex lens in a vast natural telescope. Instead of seeing one quasar, astronomers see multiple, distinct images of the exact same object arranged around the lensing galaxy in a pattern known as an Einstein cross or an Einstein ring. These aren't different quasars, they are all copies of the same single source, their light having taken slightly different paths around the gravitational well of the lensing galaxy before all converging at our telescopes. The time delay between these paths can be significant days, weeks, or even months. This means if the quasar flickers or flares, that change in brightness will appear in one image first, and then later in the others like a celestial echo. By precisely measuring these time delays, astronomers can perform an extraordinary feat. They can triangulate the geometry of the entire system and make an independent measurement of the universe's expansion rate, the Hubble constant, adding another crucial data point to the great cosmological debate. Beyond creating these beautiful multiple images, gravitational lensing also acts as a natural magnifying glass. The bending of light rays can focus them, causing the background quasar to appear dramatically brighter than it normally would. This amplification effect is a gift to astronomers, allowing them to study quasars that are so fantastically distant and faint that they would otherwise be completely invisible to our current telescopes. It's as if the universe has provided us with a built-in zoom lens, enabling us to peer into the inner workings of quasars from the very edge of the observable universe. We can resolve details in the accretion disk, study the structure of the fast-moving gas clouds near the black hole, and probe the physics of these engines with a level of precision that would be utterly impossible without this gravitational assist. This magnification is particularly crucial for understanding the earliest supermassive black holes, as it allows us to see past the glare and discern the properties of the host galaxies that are otherwise drowned out by the brilliant nuclear beacon. The scientific payoff of quasar lensing doesn't stop with studying the quasars themselves. The lensing effect is exquisitely sensitive to the total mass of the foreground galaxy, including the vast, invisible halo of dark matter that surrounds it. By carefully mapping the distortions in the quasar's light, astronomers can literally weigh the lensing galaxy and chart the distribution of its dark matter. The multiple images act as probing fingers, sensing the gravitational landscape of the lens. Any small-scale clumpiness in the dark matter halo will leave a subtle imprint on the relative brightness and positions of the lensed images. This makes lensed quasars a unique laboratory for studying the nature of dark matter itself, testing whether it is cold and clumpy as in the leading theoretical models, or whether it has other, more exotic properties. Every rare, lensed quasar system we discover is therefore a double prize, a magnified view of a distant cosmic engine, and a precise scale for weighing the invisible scaffolding that holds the universe together. Yet the story of a quasar's light doesn't end with its epic journey or the gravitational lenses it might encounter. To truly understand the engine at the heart of the maelstrom, we must learn to read the specific signatures written in its glow, And this brings us to one of the most telling and bizarre features in all of astronomy: the split personality of the gas cloud surrounding the black hole. When astronomers first obtained detailed spectra of quasars, they were stunned to find that the emission lines, those bright spikes of light that reveal the presence of specific elements like hydrogen and helium, were not sharp and narrow as they are in most cosmic objects. Instead, they were fantastically broad and fuzzy, smeared out across a huge range of wavelengths. It was as if the atoms producing this light were in a state of absolute chaos, and in a way they were. This smearing is the direct result of the Doppler effect in an environment of unimaginable violence, and it points to the existence of two distinct concentric zones of gas known as the broad line region and the narrow line region. Let's start with the inner circle of this cosmic storm, the broad line region. Picture a vast, thick swarm of gas clouds orbiting the supermassive black hole at a distance of only a few light days to a few light weeks. While that sounds like a comfortable buffer, the gravitational grip of the black hole at that range is so overpowering that these clouds are whipped into a frenzied orbit, reaching velocities of thousands, even tens of thousands of kilometers per second. That's a significant fraction of the speed of light. Now, because of the Doppler effect, the light from these clouds tells a dramatic story. The clouds moving directly toward us have their light shifted to shorter, bluer wavelengths, while the clouds moving directly away from us at the same incredible speed have their light shifted to longer, redder wavelengths. Meanwhile, all the clouds moving at tangles in between contribute to every shade in between. The net result is that a single, precise emission line from an element like hydrogen gets stretched and pulled from both the blue and the red end, merging into a single, enormously broad and blurry hump in the spectrum. This extreme broadening is our direct evidence for the terrifying orbital speeds just outside the event horizon, a clear signpost of the black hole's immense gravitational dominance. But if you look more closely at the same spectrum, you'll often find a second, much sharper set of lines superimposed on top of this broad, chaotic smear. These are the signatures of the narrow line region. This zone exists much farther out from the black hole's direct gravitational grasp, typically hundreds or even thousands of light years away, residing in the more sedate outer reaches of the galactic nucleus. Here, the gas clouds move at much more leisurely paces, a few hundred kilometers per second, speeds that are comparable to the random motions of stars within a galaxy. Because the velocity range is so much smaller, the Doppler broadening is minimal, resulting in those crisp, narrow emission lines. The presence of these two distinct regions in the same spectrum is like listening to an orchestra where the violins right in front of you are playing a furious, high-speed glissando, while the cellos at the back of the hall are holding a clear, steady note. Both are part of the same performance, but they are telling you about completely different sections of the ensemble. The existence of these two zones is not just a curiosity. It is a powerful diagnostic tool that allows astronomers to perform a kind of cosmic autopsy on the active galactic nucleus. The broad line region acts as a direct probe of the black hole's most extreme environment. By measuring the width of a broad emission line, scientists can directly calculate the velocity of the orbiting gas. Combining that velocity with an estimate of the size of the broad line region, often determined from those rapid variability studies we discussed earlier, allows them to apply the laws of gravity and weigh the central black hole itself. It's one of the primary methods used to determine the masses of these supermassive objects, revealing the true scale of the monster powering the entire show. The narrow lines, on the other hand, tell us about the larger environment. They reveal the composition and density of the more distant gas, which is often being illuminated and ionized by the intense ultraviolet radiation from the central engine. They can show us how the host galaxy's own interstellar medium is being affected, heated, and shaped by the quasar's powerful outburst. The relationship between these two regions also provides crucial clues about the structure of the accretion flow and the geometry of the entire system. The prevailing model suggests that the dense, fast-moving clouds of the broad line region are likely embedded within a more pervasive, hotter medium, possibly related to the accretion disk or a wind flowing off its surface. Their survival in such a hostile environment is a puzzle in itself, as the intense radiation pressure from the quasar should theoretically blow them apart. Their continued existence suggests they are incredibly dense, perhaps as dense as the atmospheres of stars, acting like hardy cosmic moths fluttering perilously close to an unimaginably brilliant flame. Meanwhile, the narrow line region represents the illuminated outskirts, where the galaxy's own gas reservoirs are caught in the quasar's spotlight, their atoms excited into fluorescence by the distant but still overpowering radiation. This beautiful and intricate dance of light and velocity, encoded in the simple rise and fall of a spectral line, transforms a single measurement into a multi-layered story of gravity, radiation, and structure, giving us a detailed map of a realm we can never hope to visit directly. Having peered into the heart of the quasar engine and mapped its surroundings, we are still left with a monumental puzzle that brings us to one of the most profound mysteries in modern cosmology. How did these supermassive black holes get so big so fast? This is the enigma of the giant's cradle. We've observed quasars with billion solar mass black holes shining brilliantly when the universe was less than 700 million years old. To put that in perspective, that's like finding a fully grown, towering redwood tree sprouting from a seedling in just a few days. It defies our conventional understanding of growth. If the first black holes formed from the deaths of the very first stars, they would have been relatively small, perhaps a few dozen times the mass of our Sun. For one of these stellar mass black holes to grow into a billion solar mass behemoth, it would have to feast on gas at a ferocious rate, near the theoretical maximum for its entire existence. But there's a problem. This rapid feeding itself creates intense radiation pressure that pushes back on the infalling gas, effectively putting a brake on the black hole's own growth. It's a cosmic catch-22, where the very act of eating makes it harder to swallow more food. This fundamental tension has led scientists to propose a truly bizarre and radical alternative: that the seeds for these cosmic monsters were not born from stars at all, but were instead sown directly from the primordial gas of the young universe. This concept is known as the direct collapse black hole seed. Imagine the early universe, a dark, broiling sea of hydrogen and helium gas before the first stars had flickered to life. In regions where dark matter had caused the gas to condense into exceptionally massive and dense clouds, something extraordinary could have happened. Under normal circumstances, such a cloud would fragment into countless smaller clumps, each collapsing to form a population of massive early stars. But in these special, pristine environments, a different fate was possible. If the gas cloud was prevented from cooling efficiently, perhaps because it lacked the heavy elements that act as coolants, or was bathed in a pervasive, intense ultraviolet light from nearby, it might have remained a single, monolithic entity. Without the ability to fragment, this gargantuan cloud, containing the mass of 100,000 suns or more, could have collapsed directly under its own immense gravity. There would be no supernova, no stellar fireworks, just a sudden, silent, and catastrophic gravitational failure. In one swift cosmic event, a black hole of staggering proportions would be born, not from a star's death, but from a raw, primordial cloud's direct implosion. This is the ultimate head start, a seed that is already a giant in its own right, a ready-made foundation upon which a future quasar could be built. The implications of this theory are staggering. A direct collapse seed with an initial mass 100,000 times that of our Sun sidesteps the growth problem almost entirely. It begins its life as a middleweight champion, already possessing a gravitational pull strong enough to hold onto vast reservoirs of gas against the push of its own intense radiation. It doesn't need to spend hundreds of millions of years in a frantic, maximum capacity feeding frenzy. it can grow at a more measured, yet still prodigious, pace to reach the billion solar mass mark within the first billion years of the cosmos. This provides a far more plausible pathway to the supermassive black holes we observe lighting up the early universe as brilliant quasars. It suggests that the very first structures to form might not have been stars or galaxies as we know them, but instead these dark, gravitational anchors around which the first galaxies would eventually assemble. In this inverted picture, the black hole comes first and the galaxy grows around it, a complete reversal of our traditional thinking where a galaxy forms and then a black hole slowly accumulates at its center. Of course, such a rare and specific birth process would mean that these direct collapse seeds are the cosmic equivalents of unicorns, incredibly difficult to find. They would be black holes in their infancy before they have had time to accrete enough material to shine as brilliant quasars. They would exist in a dark, quiet state, lurking in the hearts of nascent protogalaxies. Astronomers are actively hunting for these elusive objects, scanning the deepest, most ancient images from our most powerful telescopes like the James Webb Space Telescope for any telltale signature. One promising method is to look for the subtle glow of superheated gas in a very compact region, a faint whisper of accretion onto a massive object that is not yet a full-blown quasar. Another is to search for the unique chemical fingerprints in the surrounding gas, which would have been permanently altered by the intense radiation field that allowed the direct collapse to occur in the first place. Finding even one confirmed example of a direct collapse black hole seed would be a discovery of Nobel Prize-winning significance, as it would validate a key theory for the origin of cosmic structure and finally explain how the universe managed to build its most powerful engines in the blink of a cosmic eye. It would reveal a hidden chapter in the story of creation, a time when the rules of growth were rewritten by the sheer raw power of primordial gravity. This brings us to a concept in astrophysics that is as elegant as it is bizarre: the idea that the universe might be playing a cosmic shell game with us, presenting what looks like a menagerie of different monsters when in fact we might just be looking at the same beast from different sides. This is the unification model of active galactic nuclei, a powerful and compelling theory that suggests the dazzling variety of quasars, the intense blazars, and the brilliant Seyfert galaxies are not fundamentally different creatures. Instead, they could all be the same underlying structure, a supermassive black hole with an accretion disk and relativistic jets, and the only thing that changes is our viewing angle from Earth. It's a proposition that turns the chaos of classification into a matter of simple perspective, where the entire taxonomy of active galaxies is unified under a single, breathtakingly simple geometric layout. At the heart of this model lies a crucial, donut-shaped structure we haven't discussed in detail yet: the obscuring dust torus. Imagine the black hole and its glowing accretion disk at the center. Encircling this inner inferno at a much greater distance is a thick, dense ring of gas and dust, a cosmic bagel on a scale of light years. This torus is not a gentle cloud, it's an opaque wall, a fundamental piece of architecture in the active galactic nucleus. Its role in the unification scheme is absolutely critical because it acts as the ultimate blindfold. Whether we can see the brilliantly glowing central engine directly, or whether our view is blocked by this dusty wall, entirely dictates what kind of AGN we think we are observing. This simple geometric obstruction, combined with the orientation of the relativistic jets, creates the entire spectrum of phenomena we have catalogued for decades. Let's put this into practice. Picture the system from the top down, looking directly along the pole, straight down the barrel of one of the relativistic jets. From this privileged vantage point, we have an unobstructed view of the very heart of the beast. We can see the blazing accretion disk and the base of the jet pointed almost directly at us. This is what we classify as a blazar. Because the jet is aimed right at our telescopes, the effects of relativity become spectacularly pronounced. The particles in the jet, moving at over 99% of the speed of light, have their light massively boosted in our direction, an effect called relativistic beaming. This makes the blazar appear incredibly bright, and its brightness can vary violently and rapidly across all wavelengths, from radio waves to gamma rays. We are essentially staring into the universe's most powerful particle accelerator head-on, and the experience is one of overwhelming, chaotic intensity. Now let's tilt our perspective just a little. We're no longer looking directly down the jet's throat, but we still have a clear, clean line of sight to the central accretion disk. Our view is from above the obscuring torus, so the dusty bagel does not block our view of the brilliant core. In this orientation, we observe a classic quasar. We see the incredible luminosity of the accretion disk and the broad emission lines from the fast-moving gas clouds in the broadline region. But the jet is now pointed off to the side, so we don't get the full, head-on blast of its beamed radiation. The quasar is still unbelievably luminous, outshining its host galaxy, but its light is more steady and dominated by the thermal glow of the accreting material rather than the violent synchrotron radiation of the jet. It's a more balanced, though still unimaginably powerful, view of the central engine. But what happens if we view the system from the side, edge-on? This is where the dust torus truly earns its name. From this angle, the thick, opaque ring completely obscures our direct view of the central accretion disk and the innermost broad line region. We cannot see the powerhouse itself. However, the active nucleus is still there, and its intense radiation escapes vertically, above and below the plane of the torus. This radiation illuminates the more distant gas clouds in the narrow line region, which are far enough out to be visible from our side on perspective. What we see is the signature of a Seyfert galaxy, a bright galactic center with sharp, narrow emission lines, but no broad lines because our view of the fast-moving inner gas is completely blocked by the dust. The torus has hidden the central monster from our sight, allowing us to see only its distant, illuminated surroundings. In some extreme cases, if the torus is exceptionally thick and our view is perfectly edge-on, the central engine might be so completely hidden that we wouldn't even identify the galaxy as active at all using traditional optical telescopes, though it might still be detectable in infrared light as the dust itself is heated and glows. The beauty and the sheer explanatory power of the unification model is that it takes a zoo of seemingly different objects and organizes them into a single, coherent family portrait. A blazar, a quasar, and a Seyfert galaxy are not inherently different. They are the same physical object wearing different masks depending entirely on the accident of our viewpoint. This idea is supported by a wealth of observational evidence. For instance, we see the predicted types of dust absorption in the spectra of different AGN classes, exactly as the model forecast. In objects where we suspect we are looking through the torus, we find signatures of heavy obscuration, while in those we classify as face-on, the view is clear. Furthermore, statistical studies of the populations align with what we would expect from random viewing angles. We see fewer blazars than Seyfert galaxies, which makes perfect sense because the narrow cone of a jet pointed directly at us is a much rarer alignment than a more common side-on view. Of course, science is rarely that perfectly simple, and the unification model is not without its challenges and nuances. There is growing evidence that the dust torus may not be a simple, static donut. It might be a more dynamic, clumpy structure, or even a windswept fountain of material rising from the accretion disk. The model also seems to work best for the more powerful radio-loud AGN with strong jets, and there is ongoing debate about how well it unifies all the lower luminosity Seyfert types. Some astronomers propose that the intrinsic power of the central engine also plays a key role, meaning that a low-power black hole could never appear as a brilliant quasar, no matter which way we look at it. Yet, even with these refinements, the core premise remains one of the most elegant ideas in modern astrophysics. It demonstrates that what we often perceive as complexity in the cosmos can sometimes be an illusion, a trick of geometry and perspective. The universe presents us with a carnival of mirrors, and the unification model gives us the key to understanding that the many faces we see are, in the end, reflections of a single, profoundly powerful and fundamental cosmic engine. So we've seen how the unification model sorts the cosmic zoo into a single family portrait. But this central engine is not just a brilliant spectacle or a distant beacon. It's an active, violent participant in the life of its own home. This brings us to one of the most profound and game-changing realizations in modern astrophysics, the bizarre phenomenon of quasar feedback, where the black hole's feast ultimately leads to a galactic famine. For a long time, astronomers viewed the supermassive black hole as a passive resident, sitting in the center of a galaxy, simply consuming whatever came too close. The galaxy evolved on its own, forming stars from its vast gas clouds, and the black hole was just along for the ride. But we've come to understand that this relationship is far from passive. It's a violent, dynamic, and intimate dance. The black hole doesn't just live in the galaxy, it actively controls its destiny and in some cases can even end its life. The central problem this idea solves is known as the cooling flow problem. In the early universe, massive galaxies were born within enormous halos of dark matter, which gravitationally pulled in vast amounts of hot intergalactic gas. As this gas cooled, it was expected to steadily rain down into the galaxy, providing an endless fuel supply for new stars. According to simple models, these galaxies should have continued forming stars at a ferocious rate, growing to sizes far larger than any we actually observe in the present-day universe. But they didn't. Something was shutting off the star formation in these massive galaxies, and for a long time that something was a mystery. The prime suspect became the most energetic event a galaxy can host, its own active quasar. This is where the concept of feedback enters the stage. Think of it as a cosmic thermostat. The galaxy provides the fuel, the gas, that feeds the central black hole. As the black hole accretes this gas, it doesn't just convert it into light. It also unleashes a tremendous amount of energy back into the galaxy in two primary forms, radiation and powerful winds. The intense radiation from the quasar blasts out in all directions, heating the surrounding gas and preventing it from cooling and collapsing to form new stars. But the real killer punch comes from the mechanical feedback, the colossal outflows. We're not just talking about the highly focused relativistic jets, though they play a role. We're talking about galaxy-wide winds, vast streams of material being physically blasted out of the galactic core at speeds of thousands of kilometers per second. These are not gentle breezes, they are hurricanes of energy capable of sweeping an entire galaxy clean of its star-forming fuel. The mechanism behind these winds is a combination of sheer radiation pressure and thermal pressure. The quasar's light, though massless, carries immense momentum. When these photons slam into dust grains and electrons in the surrounding gas, they can physically push it outward like a sail being pushed by sunlight. At the same time, the environment around the quasar is so ferociously hot that the gas develops tremendous thermal pressure, expanding violently and explosively. The result is a galactic-scale eruption. These quasar-driven winds can eject thousands of solar masses of material every single year, and over the relatively short lifetime of the quasar phase, a few million years, they can expel a significant fraction of the entire galaxy's gas reservoir. This gas is the very raw material for future stars and for future black hole growth. By blowing it away, the quasar effectively slams the brakes on both its own food supply and the galaxy's ability to make new stars. This creates a beautiful, if terrifying, cycle of self-regulation. The more gas the galaxy has, the more the black hole eats and the brighter the quasar shines. The brighter the quasar shines, the more powerfully it heats and expels the surrounding gas. Eventually, the feedback becomes so strong that it blows away the remaining fuel, starving the black hole and causing the quasar to dim and fall silent. The galaxy, now devoid of its cool gas, enters a state of quiescence. Its stellar population ages, but no new blue stars are born, turning it into a red and dead elliptical galaxy, a cosmic graveyard where star formation has effectively ceased. The black hole, having gorged to the point of triggering its own shutdown, now sits quietly in the center, a dormant giant. This feedback loop elegantly explains why we don't see infinitely large galaxies and why the most massive galaxies in the universe today are, for the most part, no longer forming stars. Their own central black holes, during brief, brilliant quasar phases in the distant past, essentially strangled them in their cradles. The evidence for this incredible process is mounting. Astronomers have directly observed these vast outflows in action. Using powerful telescopes, they can detect the chemical signatures of elements like oxygen and carbon in the spectra of distant quasars, and they see these lines are not just broad, but are also dramatically shifted to blue wavelengths. This tells a clear story. Immense clouds of gas are moving toward us at incredible speeds, having been blown out of the galaxy entirely. In some extreme cases, these winds are so powerful that they are not just halting star formation. They are completely disrupting the galactic ecosystem, preventing the inflow of fresh gas from the intergalactic medium and leaving the galaxy isolated and cut off from future growth. It's a dramatic demonstration of how a seemingly localized phenomenon, an event happening in a region the size of our solar system, can dictate the evolution of a structure 100,000 light-years across. The quasar, in its brilliant death throes, becomes the architect of its galaxy's long, quiet future. Just when we thought we had a handle on the nature of these solitary cosmic monsters, the universe presented us with a new puzzle, the discovery of quasars that appear to come in pairs. Imagine looking through a telescope and seeing two brilliant, nearly identical quasars shining side by side in the sky, separated by a gap that seems far too small to contain two independent galactic powerhouses. This apparent cosmic companionship presents astronomers with a fascinating detective story, one with two equally bizarre and thrilling possible explanations. The first is a spectacular illusion, a trick of cosmic light born from gravitational lensing. The second, however, is a genuine cosmic dance of titans, a pair of supermassive black holes, each the core of a merged galaxy, circling each other in a slow, gravitational waltz that will one day shake the very fabric of spacetime. The more common explanation for these dazzling duos is the gravitational lensing illusion we touched on earlier. In this scenario, there isn't actually a pair of quasars at all. Instead, there is a single, distant quasar, and its light, on its long journey to Earth, passes very close to a massive foreground galaxy. The gravity of this intervening galaxy acts as a complex lens, bending the quasar's light and creating multiple images. From our vantage point, we don't see one quasar, we see two, or sometimes even four, distinct copies arranged in a beautiful, symmetric pattern around the lensing galaxy. This is the universe's ultimate magic trick, a celestial sleight of hand that confounds our initial observations. Confirming this illusion, however, is a triumph of modern astronomy. By taking incredibly detailed spectra of each apparent quasar in the pair, scientists can look for the telltale sign, identical light fingerprints. If the two specks of light show exactly the same pattern of emission lines at exactly the same redshift, they are unequivocally two images of the same single object. It's like finding two pieces of a torn photograph and matching the jagged edges perfectly. They are confirmed to be parts of a whole, but the plot thickens considerably when the spectra don't match. Astronomers have indeed found genuine, physically connected pairs of quasars, two distinct powerhouses shining simultaneously and in close proximity. These are not illusions, they are the direct result of one of the most violent and common processes in the cosmos, galaxy mergers. We live in a dynamic and evolving universe where galaxies frequently collide and merge over billions of years. Our own Milky Way is on a collision course with the Andromeda Galaxy, and in about 4 billion years, the two will merge into a single new galaxy. When two galaxies merge, they bring their central supermassive black holes along for the ride. Initially, these black holes will be separated by tens of thousands of light years. As the merger progresses, dynamical friction, a process where the black holes gravitationally interact with stars and dark matter, causes them to lose energy and sink toward the center of the newly formed combined galaxy. They eventually form a binary pair, two supermassive black holes orbiting a common center of gravity. Observing a binary black hole system where both members are actively feeding and shining as quasars is an exceptionally rare and precious find. It requires a precise and short-lived set of conditions. Both black holes need to have a plentiful supply of gas to fuel their accretion disks at the same time, lighting them up as quasars during the same narrow window of cosmic time. This dual feeding frenzy is thought to be triggered by the merger itself, as the violent gravitational interactions funnel vast amounts of gas toward both central engines. Seeing a genuine quasar pair is therefore like catching a single frame from a billion-year-long movie. It's a fleeting snapshot of two galaxies in the final stages of becoming one, their hearts both blazing with terrifying intensity before they ultimately coalesce. These systems provide direct, observational evidence for a key prediction of hierarchical galaxy formation, the idea that large galaxies are built through the mergers of smaller ones, and they show us the dramatic mechanisms that can reignite dormant black holes. The ultimate fate of these binary supermassive black holes is where the story transitions from the bizarre to the truly profound. As the pair continues to orbit, they interact with their environment, scattering stars and slinging them away through gravitational encounters. This process slowly tightens their orbit over millions of years. However, there comes a point known as the final parsec problem, where there are simply not enough stars left within their immediate vicinity to carry away more energy and angular momentum. For a long time, it was a theoretical puzzle how the black holes could get close enough to finally merge. The prevailing solution involves a third actor, a massive circumbinary disk of gas. If a large disk of gas surrounds the pair, gravitational torques from the black holes can transfer energy and angular momentum into the gas, allowing the black holes to spiral ever closer. Once they are separated by a mere fraction of a light year, their destiny is sealed by the emission of gravitational waves. This is the hunt for one of the most elusive signals in the universe. A binary supermassive black hole in its final, tight orbit is the ultimate source of gravitational waves, ripples in the fabric of spacetime itself, as predicted by Einstein. Unlike the high-frequency waves from stellar mass black hole mergers detected by LIGO and Virgo, the waves from a supermassive binary would be extremely low frequency, with periods of years or even decades. They are far too long to be detected by ground-based instruments. Instead, astronomers have turned the entire galaxy into a detector using a technique called pulsar timing arrays. They monitor the incredibly regular radio pulses from a network of millisecond pulsars spinning neutron stars that act as cosmic metronomes. As a gravitational wave passes through our region of the galaxy, it minutely stretches and squeezes the space between us and the pulsars, causing the arrival times of their pulses to vary in a specific correlated pattern. Finding this pattern is like listening for a faint cosmic hum beneath the silent symphony of the cosmos, a hum generated by the countless binary supermassive black holes merging throughout the universe. The recent announcement of compelling evidence for this gravitational wave background is a monumental step forward, strongly suggesting that these bizarre quasar pairs and their final, violent mergers are not just theoretical curiosities, but a fundamental part of the cosmic story, shaping the architecture of galaxies and filling the universe with a vibration born from the dance of the massive objects in existence. But this narrative of a solitary beacon shining in the void was missing a crucial piece of the puzzle. For all their brilliance, quasars are not isolated monsters floating in empty space. They are deeply embedded within galaxies, and the nature of these host galaxies is itself one of the most bizarre and revealing aspects of their story. When astronomers first struggled to detect the faint, fuzzy glow of the host galaxy around a quasar, it was because the quasar's light was so intense it simply drowned out everything else, like trying to see a candle flame while staring directly into the sun. But with advanced technology and clever observational techniques, we finally peeled back the blinding glare, and what we found was both shocking and transformative. Instead of residing in peaceful, well-ordered spiral galaxies like our Milky Way, many of the most powerful quasars were discovered to be living in the epicenters of cosmic train wreck galaxies in the violent throes of a major merger. Picture the serene pinwheel of a spiral galaxy, its stars orbiting in a graceful, ordered dance. Now imagine another galaxy of similar size plowing directly through it. The delicate spiral arms are shredded, transformed into great, swirling tidal tails of stars and gas flung out into the intergalactic darkness. The gravitational forces at play are so chaotic that they completely disrupt the orderly rotation of both systems, churning and mixing their stellar populations into a single, bloated, and often ellipsoidal mess. It is within this cosmic demolition derby that the quasar finds its most potent fuel. These merger events are uniquely efficient at doing one critical thing: funneling absolutely enormous amounts of gas directly toward the central supermassive black hole. In a stable, isolated spiral galaxy, most of the gas is safely settled in a rotating disk, far from the gravitational influence of the central black hole. It's like having a vast field of wheat but no way to get it to the mill. A galactic merger is the catastrophic event that builds the conveyor belt straight to the mill's entrance. The mechanism is one of beautiful, destructive physics. As the two galaxies interpenetrate and swing past each other, their mutual gravity exerts tremendous tidal forces. These forces are exceptionally effective at robbing individual gas clouds of their orbital angular momentum, essentially their sideways motion. Think of it as a cosmic brake applied on a galactic scale. Without that sideways velocity to keep them in a stable orbit, vast reservoirs of gas lose their support and begin to fall, cascading down the gravitational well toward the very center of the newly merging system. Simulations show that these events can drive over half of the entire galaxy's gas content into the inner few hundred light years in a relatively short period, cosmically speaking. This creates an incredibly dense, turbulent, and gas-rich environment right at the black hole's doorstep, providing it with a sudden, spectacular feast. The black hole, which may have been dormant and starved for eons, suddenly finds itself submerged in an ocean of fuel. It responds by accreting matter at a furious maximum rate, igniting into the brilliant quasar phase we observe from across the universe. The quasar is, therefore, not the cause of the galactic chaos, but rather the spectacular symptom of it, the brilliant flare that signals a galactic ecosystem being fundamentally reshaped. This intimate connection between mergers and quasar activity solves a major puzzle: why quasars were so much more common in the early universe. That era was a far more crowded and violent time, with galaxies packed closer together and collisions occurring with much greater frequency than they do today. The universe was a construction site, and mergers were the primary tool for building large galaxies. Every major collision provided the perfect conditions to trigger a quasar, lighting up the cosmic darkness with these brilliant beacons. As the universe expanded and galaxies grew farther apart, the rate of these dramatic mergers declined, and so too did the population of the most luminous quasars. Their brilliant light faded, not necessarily because the black holes disappeared, but because the violent, gas-funneling events that fed them became rarer. The monster in the center hadn't died. It had simply fallen asleep again, its extravagant feast over, waiting for the next cosmic delivery of fuel that for many may never come. Just when astronomers thought they had the classification of active galaxies neatly sorted by the unification model, the cosmos delivered a curveball so strange it seemed to defy the very idea of a stable universe. Welcome to the utterly bizarre world of changing-look quasars, objects that appear to rewrite their own cosmic identity right before our eyes. Imagine a brilliant quasar with its characteristic broad emission lines signifying fast-moving gas near the black hole, shining steadily for years. Then, over a period of just months or a few years, it dims dramatically, and when astronomers check its spectrum again, those broad lines have simply vanished. It hasn't just gotten fainter, its fundamental spectral fingerprint has transformed, making it look like an entirely different class of object. It's as if a roaring lion suddenly decided to become a quiet house cat, a transformation that challenges our understanding of how these immense structures operate over time. The traditional unification model, which so elegantly explained different appearances based on a stable, fixed orientation, is fundamentally a static picture. It assumes the donut-shaped dust torus and the broad line region are permanent structures. Changing-look quasars shatter that assumption by demonstrating that the central engine is far more dynamic and volatile than anyone predicted. These aren't just small fluctuations in brightness. This is a complete personality shift. A quasar that was once classified as a Type 1 with clear broad lines can transition to a Type 2 with only narrow lines and then, in some astonishing cases, change back again. This isn't a trick of perspective or a lensing illusion. This is a real, physical change happening in the heart of the galaxy, and it happens on a timescale that is, cosmically speaking, blisteringly fast. So what could possibly cause such a dramatic metamorphosis? Astrophysicists have two primary suspects, and both point to profound instabilities in the feeding habits of the supermassive black hole. The first and most compelling theory is a radical change in the accretion rate. Picture the steady stream of gas flowing into the black hole's accretion disk as a mighty river. Now imagine a giant dam being built upstream, suddenly cutting off the water supply. The river downstream shrinks to a trickle. In the quasar's case, the river is the flow of interstellar gas, and the dam could be a temporary disruption, perhaps the final consumption of a particularly large gas cloud or a complex instability within the disk itself. When the fuel supply is abruptly choked off, the inner, hottest part of the accretion disk, which is responsible for ionizing the gas clouds in the broad line region, simply cools down and dims. Without that intense ultraviolet radiation to excite them, the fast-moving gas clouds in the broad line region stop glowing, and their broad emission lines disappear from the spectrum. The central engine hasn't vanished, but it has entered a state of hibernation, its brilliant light switched off due to a lack of fuel. The second leading theory involves a moving shadow, a kind of celestial eclipse happening on a monumental scale. Instead of the fuel supply dwindling, perhaps a large, dense cloud of gas and dust from the inner region of the torus or a wind from the accretion disk itself drifts directly into our line of sight. This wouldn't be the static torus of the unification model, but a dynamic, wandering cloud. If this cloud were to pass between us and the innermost broad line region, it could act as a temporary curtain, blocking our view of the fast-moving gas and its broad emission lines. From our perspective, the quasar would appear to transform from a Type 1 to a Type 2, not because the broad line region has ceased to exist, but because we can no longer see it. The central engine might still be shining just as brightly, but its telltale signature is momentarily hidden from our view. This would be like a thick cloud passing in front of the sun. The sun hasn't changed, but its light and heat are temporarily obscured from our position on Earth. The sheer speed of these transformations is what places such tight constraints on the size of the central engine and provides the most compelling evidence for the accretion change model. Remember the light travel time argument we discussed earlier. The region responsible for the variable behavior must be small enough for changes to happen coherently across it. The fact that a quasar can dim and lose its broad lines in just a couple of years means the broad line region itself must be relatively compact. If it was spread out over thousands of light years, it would take millennia for the news of the dimming to spread throughout the entire region, and the change would appear slow and gradual to us. The rapid observed changes tell us that the broad line region is likely only light months or light years across, and that the process powering it, the accretion onto the black hole, can turn on and off on a human timescale. This paints a picture of a chaotic, turbulent, and unpredictable feeding process where the black hole's meal plan is subject to sudden feasts and famines. Discovering and monitoring these changeable beasts requires a new kind of astronomy, one that constantly watches the sky. It is large, automated time domain surveys like the Zwicky Transient Facility and the upcoming Vera-C Rubin Observatory that are now catching these cosmic chameleons in the act. By repeatedly scanning the entire sky and comparing new images to old archives, these projects can flag objects that have undergone significant changes in brightness. Follow-up observations with powerful spectrographs then confirm the spectral transformation, turning a curious dimming event into a profound discovery. Each new changing-look quasar adds a critical data point, helping scientists determine which of the two theories, accretion, shutdown, or moving clouds, is the dominant mechanism, or whether both are at play in different systems. The existence of changing-look quasars forces a major revision of our models. It tells us that the structures around supermassive black holes are not permanent, rigid fixtures, but are instead dynamic and evolving on short timescales. The dusty torus might be more of a clumpy, roiling fog than a solid ring. The accretion flow may be prone to violent instabilities, similar to water gurgling down a drain, causing it to sputter and surge. This new, dynamic picture complicates the elegant simplicity of the unification model, but it also enriches our understanding, revealing the active galactic nucleus as a living, breathing entity that can undergo dramatic mood swings. It connects the long-term life cycle of a quasar, with its million-year phases of activity and quiescence, to short-term flickers and transformations, showing us that the life of a cosmic monster is far more eventful than we ever imagined. This brilliant, violent spectacle of a quasar cannot last forever. The very nature of its power contains the seeds of its own demise, leading us to a profound realization about the life cycle of these cosmic giants. A quasar is not a permanent feature of a galaxy. It is a spectacular, fleeting phase, a brief fireworks display in a cosmic timeline that spans billions of years. The most brilliant quasars, those that outshine their entire galaxies, are likely only active for a relatively short burst of between 10 and 100 million years. This might sound like an eternity to us, but on the scale of a galaxy's 10 billion-year life, it is merely a blink of an eye. This transient existence is dictated by a simple, brutal equation of supply and demand. The black hole's appetite is voracious, and the reservoir of cold, dense gas required to feed it is finite. Even the vast amounts of gas funneled inward during a galactic merger will eventually be consumed or, as we learned with feedback, violently expelled. The quasar phase is the black hole's grand feast, but every feast must eventually come to an end when the pantry is bare. When the fuel supply is finally exhausted, the brilliant engine sputters and dies. The accretion disk, deprived of fresh material, thins out and cools, its fierce glow fading from an incandescent blaze to a dim ember. The broad line region, no longer bathed in intense ultraviolet radiation, winks out of existence. The relativistic-jets, starved of their power source, cease their flow and gradually dissipate into the intergalactic medium. What remains is a dormant supermassive black hole, a sleeping giant sitting in silence at the heart of its galaxy. The galaxy itself, often stripped of its star-forming gas by the quasar's final feedback-driven winds, may enter a long, quiet period of passive evolution, its stellar population aging without the birth of new stars. This is the death of the quasar, not the destruction of the black hole, but the end of its period of brilliant, visible activity. It becomes an invisible gravitational anchor, a ghost of its former self waiting in the darkness. But the story doesn't necessarily end there. The cosmos is a place of constant motion and unexpected deliveries, and this leads to one of the most thrilling possibilities in galactic astronomy, the rebirth of a quasar. A dormant black hole, even one that has been silent for hundreds of millions of years, is always hungry. It is a gravitational pitfall, forever waiting for a new supply of fuel to stumble into its grasp. There are several ways this cosmic delivery can happen, each capable of reigniting the brilliant engine. The most dramatic is a new galactic merger. If another gas-rich galaxy ventures too close and is captured by the dormant galaxy's gravity, the same violent gas funneling process that triggered the first quasar phase can begin all over again. The incoming galaxy acts as a cosmic caterer, delivering a fresh, massive supply of gas directly to the black hole's doorstep, restarting the entire cycle of accretion, brilliant light, and powerful outflows. Another, more subtle method of reignition can occur without a full-scale merger. Over vast timescales, a galaxy can slowly accrete gas from the intergalactic medium, or internal processes like stellar winds from aging stars can gradually replenish the central reservoirs. If this gas can somehow lose its angular momentum and trickle down to the very center, it could provide enough sustenance to wake the black hole from its slumber. We might not see the full-blown brilliance of a classic quasar in this case, but a lower-level activation, turning the dormant giant into a less luminous active galactic nucleus like a Seyfert galaxy. This means a single supermassive black hole could potentially go through multiple cycles of activity and quiescence throughout its life, flickering on and off like a cosmic lighthouse depending on the availability of fuel in its immediate environment. Its life is not a single, brilliant flash, but a series of energetic outbursts punctuated by long periods of silence. This cyclical view transforms our understanding of a galaxy's central engine from a static object into a dynamic, breathing heart. The quasar phase is the galaxy's feverish, energetic peak, a time of tremendous growth and self-regulation that shapes its future. The dormant phase is its rest, a period of consolidation and stability. Evidence for this rebirth cycle is etched into the skies. Astronomers have identified galaxies that show clear signs of multiple, distinct episodes of star formation and activity in their structures. Some large elliptical galaxies possess faint outer shells or tidal tails, the ghostly remnants of an ancient merger that likely fueled a quasar outburst billions of years ago. Meanwhile, their central regions might show signs of more recent, low-level activity, suggesting the black hole has been recently snacking on a smaller gas delivery. Each reignition event, however, is likely less potent than the last. As a galaxy ages and its gas is consumed and expelled, the available fuel for future feasts diminishes. The first quasar phase might be the most spectacular, with subsequent reactivations being shorter, dimmer echoes of that initial glorious outburst. This cyclical nature also provides a powerful answer to a long-standing question. Why do we see so few quasars in our local universe compared to the distant, early cosmos? The answer is that the golden age of quasars was the era of peak construction, when galaxies were frequently merging and gas was abundant. That era is largely over. In today's universe, such violent, gas-rich mergers are far less common. Most supermassive black holes in our cosmic neighborhood, including the one at the center of our own Milky Way, are in a quiet, dormant state. Their brilliant quasar phases a distant memory from a more violent and energetic youth. They are retired giants, their immense power now latent. The cycle of quasar death and potential rebirth is a testament to the dynamic, ever-changing nature of the cosmos. It tells us that even the most powerful objects in the universe are subject to the rhythms of supply and demand, and that a silent, dark giant today could, given the right cosmic circumstances, once again blaze forth as a beacon that outshines the light of every star in its home. To truly grasp the physics behind those unimaginable jets screaming across the cosmos, we have to venture beyond the accretion disk and into the very spin of the monster itself. We've talked about the black hole's gravity pulling matter in, but its rotation is an equally formidable source of power, and tapping into it requires one of the most fundamental forces in the universe. This brings us to the truly mind-bending concept known as the Blandford-Zenagic process, a theoretical mechanism that sounds like it's straight out of an advanced physics textbook, but may well be the exclusive engine for the most powerful jets we observe. The central idea is audacious. Instead of just using the gravitational energy of infalling matter, this process directly extracts the rotational energy of the black hole itself, using magnetic fields as the ultimate cosmic transmission. Picture a spinning black hole dragging the fabric of spacetime around with it in a vortex known as its ergosphere. Now, imagine that this black hole is threaded with immensely powerful magnetic field lines, anchored not in the black hole itself, since nothing, not even information, can escape from within the event horizon, but in the incredibly hot, ionized plasma of the inner accretion disk. As the black hole spins, it twists these magnetic field lines into a tightly wound, coiled spring of energy. The rotating spacetime acts like a gigantic dynamo, inducing unimaginable voltages along these field lines. In the Blandford-Zenagic process, this coiled magnetic spring does something extraordinary. It acts as a conduit, carrying energy and angular momentum directly away from the black hole. The twisted magnetic fields essentially grip the spinning spacetime and fling plasma outward, launching it along the black hole's rotational axis at velocities achingly close to the speed of light. It's a bit like using the black hole's own spin to power a cosmic slingshot, with magnetic fields providing the rubber band. What makes this process so efficient and bizarre is that it converts the pure rotational energy of the black hole into a directed outflow with almost perfect efficacy. Theoretical work suggests this could be the most efficient energy extraction mechanism known to physics, far surpassing nuclear fusion or even the gravitational energy release from accretion. In essence, a rapidly spinning black hole surrounded by a strong magnetic field becomes a battery, and the Blandford-Zenagic process is the circuit that allows us to plug into it. This could explain why some jets are so phenomenally powerful and persistent over millions of years. They are fueled not just by the finite amount of gas falling in, but by the immense spinning inertia of the black hole itself, a reservoir of energy that can be slowly drained over cosmic timescales. The jet becomes the black hole's way of shedding its own spin, a brilliant and violent release of its rotational vitality. Of course, such an extreme process doesn't work in isolation. It requires a perfect and perfectly powerful partnership with the accretion disk. The magnetic fields that are so crucial to the mechanism aren't generated by the black hole. They are generated by the churning, dynamo action of the accretion disk itself. The ionized gas in the disk is a superb conductor, and its differential rotation inner parts orbiting much faster than outer parts winds up weak initial magnetic fields, amplifying them to phenomenal strength. Think of it as a self-exciting cosmic generator. The disk creates the powerful magnetic fields, and those fields then thread the black hole, enabling the Blandford-Zenagic process to tap the hole's spin. This creates a fascinating feedback loop. A more massive and energetic accretion disk can generate stronger magnetic fields, which in turn can extract more rotational energy from the black hole, powering even more formidable jets. This intimate connection might also explain the different types of radio-loud and radio-quiet active galaxies. Perhaps the presence of a strong, large-scale magnetic field anchored in the disk is the key ingredient that determines whether a black hole can launch these spectacular relativistic outflows. The evidence for this complex magnetic dance, while indirect, is becoming increasingly compelling. Sophisticated computer simulations that model the magnetohydrodynamics of plasma around spinning black holes consistently show that the Blandford-Zienagic process is not just a theoretical fantasy. It naturally emerges as the dominant mechanism for jet formation in systems with the right conditions. These simulations show the magnetic field lines becoming tightly wound into a helical structure, forming a rigid, rotating column that channels and collimates the outflow. Furthermore, observations of the polarization of light from jets, the specific direction in which their light waves oscillate, reveal the telltale signature of incredibly strong, organized magnetic fields guiding the flow. The sheer stability and focus of jets over millions of light years is itself a powerful argument for a mechanism like Blandford-Zienagic, as only magnetic confinement could prevent such a high-energy plasma from dispersing almost instantly into the void. While we may never drill down into the ergosphere of a supermassive black hole to take direct measurements, the ghostly imprint of these magnetic giants is written across the universe in the brilliant, straight lines of the most powerful jets ever seen. Yet this intricate cosmic barcode leads us to an even more powerful application, where the quasar becomes less the object of study and more the ultimate flashlight, illuminating the vast, invisible emptiness between the galaxies themselves. If we want to understand the universe's architecture, we cannot just look at the bright cities of stars. We must also survey the dark, sprawling countryside that connects them. This brings us to the profound use of quasars as cosmic probes of the intergalactic medium. The space between galaxies is not a perfect vacuum. It is sparsely populated with an incredibly diffuse and primordial gas, primarily hydrogen and helium, which constitutes the true bulk of the universe's normal matter. This intergalactic medium is so faint and thin that it emits virtually no light of its own, rendering it completely invisible to direct observation. To study it, astronomers needed a brilliant, distant light source shining through it, and there is no flashlight more powerful than a quasar. The technique is conceptually beautiful in its simplicity. It relies on the same physical principle that lets a botanist study the internal structure of a leaf by holding it up to the sun. The quasar acts as that brilliant sun, and the diffuse gas of the intergalactic medium is the leaf. As the quasar's light travels for billions of years across the cosmos, it passes through this pervasive network of gas. Whenever the light encounters a cloud or a filament of neutral hydrogen, the atoms within that cloud act like tiny filters, absorbing light at their specific resonant wavelength, the Lyman alpha line in the far ultraviolet. Each cloud imprints a single, sharp, dark absorption line onto the quasar's spectrum at a wavelength corresponding to that cloud's particular distance from us. Because the universe is expanding, a cloud that is farther away is receding from us faster, and its absorption line is redshifted to a longer wavelength. The result is what we first explored as the Lyman alpha forest, a spectacularly dense series of thousands of absorption lines, each one a shadow cast by a separate cloud of hydrogen at a unique snapshot in cosmic history. By meticulously decoding this forest, astronomers can construct a three-dimensional core sample of the universe's large-scale structure. A single quasar spectrum gives us a one-dimensional skewer, a pencil-thin beam of insight stretching all the way back to the quasar itself. But by observing hundreds or thousands of quasars scattered across the sky, we can assemble a colossal tomographic map. We can see how the tenuous gas is distributed, revealing the cosmic web in stunning detail. This web is the fundamental scaffolding of the cosmos, a vast network of dark matter filaments along which normal matter has condensed. The Lyman alpha forest shows us that the intergalactic medium is not smooth. It is a frothy, filamentary structure with denser knots where galaxies are forming and vast, empty voids in between. This map confirms the predictions of our best cosmological models, providing direct observational evidence for the growth of structure over billions of years. Furthermore, this technique allows us to witness the evolution of the intergalactic medium itself. When we look at the spectra of very distant, high redshift quasars, those whose light comes from when the universe was only a billion years old, the Lyman alpha forest is incredibly dense. The absorption lines are so numerous that they blend together into a continuous trough, known as the Gunn-Peterson trough, indicating that a significant fraction of the intergalactic hydrogen was still neutral at that early epoch. As we look at quasars that are closer and more recent, the forest becomes sparser. This thinning out tells a dramatic story, the epoch of reionization. Sometime during the first billion years, the intense ultraviolet radiation from the first generations of stars and quasars flooded the universe, stripping the electrons from the hydrogen atoms in a vast cosmic-scale ionization event. The intergalactic medium was transformed from a neutral fog into a transparent, ionized plasma. The evolving density of the Lyman alpha forest is our primary record of this pivotal transition, charting how the universe's dark ages ended and the cosmos became clear for light to travel freely. The utility of these cosmic probes extends beyond just mapping hydrogen. The same absorption lines can reveal the presence of other, heavier elements like carbon, silicon, and oxygen woven into the intergalactic medium. This is a startling discovery because these elements could only have been forged in the nuclear furnaces of stars and then scattered into intergalactic space by supernova explosions or powerful galactic winds. Finding their signatures in the Lyman alpha forest means that the vast voids between galaxies have been chemically polluted by earlier generations of stars. This intergalactic pollution tells us that galaxies are not closed systems. They are leaky, constantly exchanging matter with their surroundings through these powerful feedback processes. The quasar's light, therefore, acts as a sensitive chemical sensor, allowing us to take a core sample of the universe's metallicity and trace the history of star formation across cosmic time, all from the shadows cast on a brilliant beacon from the dawn of creation. But for all our sophisticated theories and observations, we are still faced with a fundamental, almost philosophical limitation. We are trying to understand a cosmic engine that is, in practical terms, a dimensionless point of light. Even the most powerful telescopes cannot resolve the central engine of a quasar. The region is simply too small and too mind-bogglingly far away. We are like doctors trying to diagnose a patient's heart by observing the flicker of a candle flame from miles away. The brilliance is unmistakable, but the intricate details of the machinery producing it remain hidden in a blur of distance. This is the core challenge that has forced astronomers to become cosmic detectives, developing ingenious, indirect methods to probe the unseen. One of the most powerful of these techniques is a form of celestial echolocation known as reverberation mapping, a method that turns the inherent variability of quasars into a precise measuring tape. The principle behind reverberation mapping is as elegant as it is clever. It relies on the predictable delay or reverberation between two related events. Imagine standing in a vast, dark cavern and shouting. You hear your voice echo back a moment later. The time delay between your shout and the echo tells you the distance to the far wall. Sound travels at a known speed, so distance equals speed multiplied by time. Reverberation mapping applies this same logic to light, but instead of sound and a wall, we use the quasar's own flickering light and the clouds of gas that surround it. Here's how it works. The central accretion disk, with its intensely hot plasma, is the primary source of the quasar's continuum light, the broad-spectrum, white light glow that forms the foundation of its brilliance. This continuum light is highly variable. It brightens and dims seemingly at random. But this light also serves another purpose. Its intense ultraviolet photons are what excite and ionize the gas clouds in the surrounding broadline region, causing them to fluoresce and emit their own specific, sharp emission lines. Now, here is the crucial part. When the continuum light from the accretion disk flares up, it takes a finite amount of time for that increased intensity of ionizing radiation to travel out to the broadline region and cause those gas clouds to respond with a flare of their own in their emission lines. There is a time lag. By meticulously monitoring a quasar for months or even years, measuring both the flickering of the continuum light and the subsequent flickering of a specific broad emission line, like the hydrogen alpha line, astronomers can measure this precise time delay. Since light travels at a constant known speed, this measured time lag directly gives us the light travel distance between the accretion disk and the broad line region. It's a direct geometric measurement of the size of the heart of the quasar. We are, in effect, using the echo of light to map the geometry of a region we could never hope to see directly. The scientific payoff from this technique is immense. By measuring the size of the broadline region and combining it with the width of the broad emission lines, which tells us the velocity of the orbiting gas, astronomers can directly calculate the mass of the central supermassive black hole using simple Newtonian physics. It's one of the most reliable methods we have for weighing these distant monsters. Furthermore, by applying this technique to different emission lines that come from different elements, each with their own unique time lags, we can start to build up a three-dimensional picture of the broadline region. We can determine that some elements are found in clouds that orbit closer to the black hole, while others are in clouds farther out, revealing a structured, stratified environment. This transforms the broadline region from a vague, blurry concept into a quantifiable physical structure with a known size and dynamics, all deduced from the careful timing of cosmic echoes. Yet, as powerful as reverberation mapping is, it still provides an indirect, averaged picture. What we truly crave is a direct image, a photograph of the beast itself. This dream is what drives one of the most ambitious projects in the history of science, the Event Horizon Telescope, or EIT. You may remember the EHT from its historic first image of the shadow of the black hole at the center of the galaxy M87. That staggering achievement was a proof of concept, demonstrating that it is possible to resolve the immediate environment of a black hole by creating a virtual telescope the size of the entire Earth. The technique, known as Very Long Baseline Interferometry, or VLBI, synchronizes radio telescopes across the globe to act as a single gigantic dish. The resolution of a telescope is determined by its diameter. The larger the dish, the finer the details it can see. By combining signals from telescopes from the South Pole to Hawaii, to Europe and the Americas, the EHT achieves an angular resolution so sharp it could, in theory, read a newspaper in New York while standing in Paris. The ultimate goal for the EHT is not just to image the black hole in a relatively quiet galaxy like M87, but to eventually turn its unparalleled resolution towards a nearby active galactic nucleus. Imagine pointing this Earth-sized eye at Centaurus A, a bright and active galaxy, or perhaps even the engine at the heart of our own galactic center, Sagittarius, a star, which is a much quieter, low-luminosity version of an AGN. While imaging a brilliant, distant quasar is still beyond its current capabilities due to their incredible distance, studying a closer AGN would be revolutionary. A direct image of the area around the black hole in an active galaxy would allow us to see in detail the base of those relativistic jets as they are launched. We could potentially distinguish the bright, swirling accretion disk from the darker, shadowed region of the black hole's event horizon. We could test the predictions of the Blandford-Zenagic process by observing the structure of the magnetic fields at the jet's origin and see how they are twisted by the black hole's spin. The potential discoveries are breathtaking. We could witness material actually crossing the event horizon, vanishing from the observable universe. We could study the intricate dynamics of the innermost stable circular orbit, the point of no return for material in the accretion disk, providing a direct test of general relativity in the most extreme gravitational environment possible. We could even watch as flares of material, perhaps similar to those that cause changing-look quasars, unfold in real time, tracing their path from the disk into the jet or down into the black hole. The AHT would move us from the realm of inference and echolocation into the era of direct observation, transforming our understanding of these central engines from a collection of cleverly deduced models into a detailed empirical map. It would be the ultimate validation, or perhaps revolution, of a century of astrophysical theory, allowing us to finally gaze directly into the violent, beautiful, and chaotic heart of the cosmic storm. But as we push our understanding of these cosmic engines to the limit, we encounter a mystery that rains down upon Earth from the deepest reaches of space, a phenomenon so energetic it defies our most powerful human-made machines. This brings us to the truly bizarre possibility that active galactic nuclei are the universe's ultimate particle accelerators, responsible for the most violent subatomic hailstorm imaginable, ultra-high-energy cosmic rays. Picture the most advanced particle physics facility on Earth, the Large Hadron Collider, where we smash protons together at velocities infinitesimally close to the speed of light to probe the fundamental secrets of matter. Now imagine a single subatomic particle, a proton or the nucleus of an atom arriving from deep space that carries kinetic energy millions of times greater than anything the LHC can ever produce. This isn't science fiction. These particles are real. They are detected hitting our atmosphere, and their existence presents one of the most enduring puzzles in all of modern physics. Where in the cosmos could nature possibly concoct such an unimaginably powerful cannon? The quest to find the source of these ghostly bullets has led astrophysicists directly to the most violent environments we know, and the relativistic jets of active galactic nuclei are prime suspects. The mechanism at work is a natural version of a process we use in particle accelerators, but scaled up to a mind-numbing degree. It's called Fermi acceleration, or more poetically, diffusive shock acceleration. Imagine a subatomic particle like a proton caught in the turbulent, magnetized maelstrom within a quasar's jet. This particle bounces back and forth, trapped by magnetic fields like a pinball between two converging supersonic shock waves moving through the jet. Each time the particle crosses a shock front, it gains a little more speed, a little more energy. It's akin to a tennis ball being volleyed back and forth between two rackets that are rapidly moving toward each other. With each impact, the ball flies faster and faster. In the chaotic interior of an AGN jet, a particle can undergo this process not just a few times, but countless times, being accelerated to velocities so extreme that its energy reaches a level we can scarcely comprehend. What makes AGN jets such perfect candidates for this role is the sheer scale of the energy reservoir they provide. The kinetic energy locked up in a jet moving at 99.9% the speed of light is almost beyond calculation. The magnetic fields within them are colossal, providing the perfect walls for this cosmic pinball machine, containing the particles long enough for them to be boosted to these phenomenal energies. Furthermore, the jets provide a continuous supply of raw material protons and atomic nuclei ripped from the surrounding accretion disk or the host galaxy's interstellar medium. These particles are then injected into the acceleration zone, where the shock waves, perhaps generated by instabilities or collisions within the jet itself, do their work. The process is so efficient that it can theoretically push individual particles to energies exceeding 100 million trillion electron volts. To put that number in perspective, that's the kinetic energy of a professionally thrown baseball, packed into a single subatomic particle smaller than an atom. The sheer concentration of force is both terrifying and beautiful, yet detecting the source of these particles is notoriously difficult, which is why this phenomenon remains a hypothesis rather than a proven fact. The problem is that cosmic rays are charged particles, and as they travel across the galaxy and intergalactic space, their paths are bent and scrambled by the weak but pervasive magnetic fields that fill the cosmos. By the time a shower of secondary particles, created when a cosmic ray smashes into our upper atmosphere, reaches our detectors on Earth, we have lost all information about the original direction it came from. It's like trying to find the source of a particular raindrop in a hurricane. The path is far too tangled to trace back. This is why we call them cosmic rays rather than cosmic lasers. They do not travel in straight, traceable lines. For decades, this has been the central challenge, leaving us with a profound mystery. We know these incredible particles exist, but we cannot easily point to their origin. The search for answers, however, is undergoing a revolution, moving from studying the particles themselves to detecting the messengers that do travel in straight lines, light and neutrinos. When an ultra-high-energy cosmic ray interacts with the cosmic microwave background, the faint afterglow of the Big Bang that permeates all of space, it can create a cascade of new particles, including high-energy gamma rays and neutrinos. Astrophysicists are now using giant neutrino telescopes, like ice cube buried deep in the Antarctic ice, to hunt for these elusive particles. A neutrino, being electrically neutral, flies straight through the universe unaffected by magnetic fields. If a high-energy neutrino can be traced back to a specific point in the sky, and that point coincides with a known blazar, an AGN with its jet pointed directly at us, it would be the smoking gun. It would provide compelling, multi-messenger evidence that we have finally located one of the universe's most powerful natural accelerators. Each detection is a piece of a cosmic forensic puzzle, bringing us closer to understanding not only the engines that power quasars but also the fundamental limits of particle physics in the most extreme environments the cosmos has to offer. But the story of a quasar's light doesn't always end when it fades from our direct view. Sometimes it leaves a ghostly imprint on the cosmos, a memory of its past violence etched into the surrounding dust. This brings us to the strange and beautiful phenomenon of the quasar light echo. Imagine standing in a vast, dark canyon and letting out a powerful shout. The sound waves travel outward, hit the distant canyon walls, and bounce back to you seconds later as a distinct echo. Now, replace the shout with a colossal flash of light from a quasar, and the canyon walls with immense, light-year-wide clouds of interstellar dust. What you get is a cosmic echo, not of sound, but of light itself, allowing us to literally look into the past and witness the ghost of a quasar's fury long after the initial explosion has subsided. Here's how this celestial memory works. At the heart of an active galaxy, the supermassive black hole doesn't always consume matter at a steady rate. Occasionally, it experiences a tremendous flare, a sudden, dramatic surge in brightness. This could be triggered by a particularly large star being torn apart and consumed, or a massive instability in the accretion disk dumping a huge amount of material onto the black hole at once. For a brief period, the quasar can become orders of magnitude brighter, unleashing a furious pulse of ultraviolet and X-ray light that explodes outward in all directions at, of course, the speed of light. The first light from this flash travels directly to our telescopes, and we record the flare as it happens, but that's only the beginning of the story. This initial pulse is just the direct beam. The real magic begins as that expanding shell of light continues its journey into the galaxy. Light travels fast, but space is immense. Surrounding the central quasar, often hundreds or even thousands of light-years away, are vast, dark clouds of cosmic dust, fine, sooty particles of carbon and silicate. When the wall of light from the ancient flare finally reaches one of these distant dust clouds, something remarkable happens. It illuminates it. The intense radiation heats the dust grains, causing them to glow brightly in the infrared, and some of the light is also reflected, much like a car's headlights illuminating fog. From our perspective on Earth, we first saw the initial flare when its direct light reached us. Then, years, decades, or even centuries later, we see a second separate event, a brightening ring or shell of infrared light that appears to expand outward from the quasar's location. This is the light echo. We are not seeing the dust cloud itself light up in real time. We are seeing it re-emit and reflect light from a flash that actually occurred in the distant past. It is a delayed broadcast of a historical event, a cosmic replay button that gives us a second chance to study a momentary cataclysm. This time-delayed nature is what makes light echoes such a powerful tool for astronomers. Let's say a quasar had a major outburst in the year 1750. The direct light from that flare would have arrived at Earth in 1750, but if there were no telescopes powerful enough to see it, the event would have passed unnoticed, lost to history. However, if that expanding shell of light from the 1750 flare is now, in our modern era, beginning to illuminate a dust cloud that is 400 light-years away from the black hole, the echo of that event is only just reaching us now. We have a second chance to observe it. By analyzing the spectrum of this echoed light, we can determine the nature of that long-ago flare, how energetic it was, what elements were involved, and how the quasar's engine behaved during that extreme moment. It's a form of astronomical archaeology, digging through layers of space and time to uncover the hidden history of a galaxy's active heart. The geometry of a light echo is equally fascinating and provides crucial information about the structure of the galactic environment. The echo doesn't appear as a full sphere. We typically see a brightening ring that seems to grow larger with time. This is because we are observing a three-dimensional structure in 2 dimensions. The flash of light expands as a thin, spherical shell. The dust clouds that produce the most visible echo are those located in a position where the path length from the flare to the dust, and then from the dust to our telescopes, creates a specific time delay. As time passes, the shell of light intersects dust clouds at progressively larger distances, making the echo appear to move outward. By meticulously measuring the expansion rate of this ghostly ring, astronomers can precisely calculate the distance to the dust clouds themselves, mapping the otherwise invisible architecture of the galaxy's interstellar medium. Each new echo is like a sonar ping, revealing the contours of the hidden landscape surrounding the quasar. Perhaps the most profound implication of light echoes is their ability to catch fleeting events that we otherwise would have completely missed. Many quasars are volatile, and their most dramatic outbursts might be rare, unpredictable, and short-lived. Without the persistent, patient eye of modern all-sky surveys, a brilliant flare from a distant galaxy could easily go unrecorded. But a light echo can preserve the memory of that flare for centuries, giving us an opportunity to discover it long after the fact. It allows us to build a historical record of a quasar's activity, showing us that what we perceive today as a steady or quiet object may have had a violently explosive past. This forces us to reconsider the life cycle of these cosmic engines. Their periods of activity are not always smooth, but are likely punctuated by these tremendous, eruptive events that shape their surroundings and their own growth in ways we are only beginning to understand. The faint, expanding whisper of a light echo is therefore more than just a pretty ghost. It is a vital clue, a time capsule that carries within it the secrets of a quasar's most violent and defining moments. Now we arrive at a cosmic detective story with a conspicuous missing person, or rather, a missing type of person. For all the incredible variety of black holes we've discovered, there appears to be a strange and persistent gap in the population, a gap that challenges our understanding of how the very first quasars got their start. On one end of the scale, we have stellar mass black holes. These are the remnants of massive stars that have gone supernova, typically weighing in at between about 5 and 100 times the mass of our Sun. We've found many of these through their gravitational waves and their X-ray signatures in binary systems. On the far opposite end, we have the supermassive black holes, the monsters weighing millions or billions of solar masses that power quasars and sit at the center of nearly every large galaxy. The logical assumption would be that there's a smooth progression between these two extremes, that there should be a whole population of intermediate mass black holes, the so-called middleweights, with masses ranging from a few hundred to a few 100,000 suns. These would be the crucial stepping stones, the missing links that show how a small seed grows into a cosmic giant. The problem is, they are incredibly, bafflingly elusive. Finding these middleweights is not just an exercise in cosmic cataloging, it's central to solving the puzzle of the early quasars. If the first black holes were born from the deaths of the first stars, they started out as stellar mass objects. For them to grow into billion solar mass behemoths in less than a billion years, they would have needed to merge with other black holes and accrete gas at a ferocious, almost maximum rate. Intermediate mass black holes are the predicted intermediaries in this process. They should be the products of countless mergers in the dense cores of young star clusters, or perhaps the direct collapse seeds we discussed earlier. Yet, when we go looking for them, the evidence is sparse and often controversial. We have a handful of promising candidates, often found in the hearts of dense globular clusters or in the faint dwarf galaxies that are the building blocks of larger ones. But these detections are like catching a glimpse of a rare animal in a dense fog. The signals are faint, and alternative explanations often exist. The sheer lack of a clear, abundant population of these middleweight black holes suggests that our standard picture of gradual, hierarchical growth might be missing a crucial piece of the puzzle. This absence forces us to consider a much more dramatic and rapid growth scenario. Perhaps the first supermassive black holes didn't grow slowly and steadily by consuming these middleweights. Instead, they may have bypassed that stage almost entirely through a process known as super-Eddington accretion. The Eddington limit is a theoretical ceiling that describes the maximum rate at which a black hole can sustainably accrete matter. When matter falls in too quickly, the intense radiation pressure it generates actually pushes back on the infalling gas, like a cosmic wind that blows away your own food supply. But what if, in the uniquely dense and chaotic conditions of the early universe, black holes could briefly exceed this limit? In a super-Eddington state, the accretion disk becomes incredibly thick and puffy, trapping its own radiation and allowing vast quantities of gas to fall directly onto the black hole in a continuous, near-catastrophic collapse. Think of it not as a steady stream of water flowing into a drain, but as a sudden, massive sinkhole opening up and swallowing an entire lake all at once. This runaway feeding frenzy could allow a stellar mass seed to balloon into a supermassive giant in a remarkably short period of time, leaving very few intermediate mass remnants behind because the phase was so brief. Another compelling possibility is that the middleweights are not missing at all, but are simply hiding in plain sight. They might be residing in environments where they are very difficult to detect. A black hole of a few thousand solar masses that is not actively accreting gas would be virtually invisible against the bright background of its host galaxy. Its gravitational influence would only be noticeable if it were orbiting extremely close to other stars, which is a rare and difficult scenario to observe. Furthermore, if these intermediate black holes were ejected from the dense star clusters where they formed due to gravitational interactions, they could now be drifting dark and silent through the vast, empty intergalactic voids. We would have no way of seeing these lone wanderers with our current technology. Their elusiveness might not be a sign of their absence, but a testament to the sheer size and darkness of the universe, which can easily conceal objects that aren't actively screaming their presence to the cosmos with brilliant light or powerful gravitational waves. The hunt for these missing middleweights is more than just an academic exercise. It's a fundamental test of our models of cosmic structure formation. The recent discoveries by gravitational wave observatories like LIGO and Virgo have added a fascinating new twist. Some of the black hole mergers they've detected fall into a mass range that is arguably intermediate, heavier than any known stellar remnant, yet lighter than a confirmed supermassive object. Are these the long-sought middleweights finally revealing themselves not through light, but through ripples in spacetime? Each new detection helps to fill in the mass spectrum, providing crucial data points. As our telescopes become more sensitive and our gravitational wave detectors more advanced, we are slowly piecing together this family portrait of black holes. The mystery of the missing middleweights remains one of the most intriguing in modern astrophysics, a quiet enigma that forces us to question whether the path to becoming a cosmic giant is a slow, steady climb or a sudden, spectacular leap. This brings us to a phenomenon that shifts our perspective from the purely cosmic to the profoundly existential. We've explored quasars as brilliant beacons and powerful engines, but we must now confront their role as potential cosmic exterminators. The very radiation that makes them visible across the universe is also a sterilizing force of unimaginable power, and this forces us to consider a startling possibility. The tranquil cosmic neighborhood we enjoy may be the exception rather than the rule, a necessary condition for life to ever gain a foothold. To understand this, we need to scale down the immense energies we've been discussing and bring them home. Imagine if the supermassive black hole at the center of our own Milky Way, Sagittarius a star, were not the quiet, dormant giant it is today, but instead a brilliant, full-blown quasar. The night sky would be utterly transformed. A single, blazing point of light would outshine the full moon, casting sharp shadows on Earth even during the night. But this new celestial wonder would be a herald of doom, not beauty. The primary threat from a nearby active quasar wouldn't be the visible light, as intense as it would be. The real danger lies in the high-energy radiation that our atmosphere thankfully shields us from under normal circumstances. A quasar in our galactic center would flood our entire solar system with a continuous torrent of X-rays and gamma rays. These high-energy photons are like microscopic bullets capable of shredding the complex molecules that constitute life. They would rip through planetary atmospheres, breaking apart the delicate bonds of nitrogen and oxygen molecules and creating a toxic smog of nitrogen oxides. This would effectively dissolve the protective ozone layer that shelters Earth's surface from the sun's own ultraviolet radiation, leaving any life on land completely exposed to a double-barreled assault from both the quasar and our own star. The surface of our planet and every other planet in the galaxy within the quasar's line of sight would become a radioactive frying pan, sterilized of all but the most hardened subsurface microbes. But the devastation wouldn't stop with radiation. The colossal outburst would also launch vast, fast-moving shells of plasma, the same material that forms the relativistic-jets, but in a less focused, more spherical explosion. If our solar system were caught in the path of such a blast, the consequences would be apocalyptic on a scale that makes all previous mass extinctions look trivial. This wave of million-degree gas would take thousands of years to travel from the galactic center to our location. But when it arrived, it would compress the heliosphere, the protective bubble of the solar wind that surrounds our entire solar system. Energetic particles from the quasar would then have direct access to the inner planets, further bombarding them with radiation. The plasma cloud itself would then sweep through, potentially stripping away planetary atmospheres entirely through intense erosion, leaving worlds like Earth and Mars as barren, airless rocks, their oceans boiled away into space. The entire galactic habitable zone, the region where conditions are right for life, would be temporarily annihilated, resetting the biological clock for thousands of light years in every direction. This grim scenario is not just speculative fiction. It is a standard part of the life cycle of many galaxies. The brilliant quasar phase is often the event that terminates a galaxy's most active period of star formation, not only by blowing away the gas but also by systematically sterilizing any planetary systems that may have been forming in its spiral arms. This paints a startling picture of cosmic evolution, where the birth of a brilliant beacon of light is inextricably linked to the death of biological potential on an unimaginable scale. It suggests that the universe may be constantly flickering with these life-extinguishing events, creating brief, localized oases of habitability in between the violent outbursts from the central black hole. The evolution of complex life requires not just a stable star and a well-placed planet, but also a quiescent galactic center, a rare and precious period of peace in an otherwise violent cosmic arena. This leads to a profound, almost philosophical implication known as the anthropic principle. In its weakest form, this principle simply observes that the universe we observe must be compatible with our existence as observers. We find ourselves in a galaxy with a quiet central black hole, not because this is the norm, but because we could not possibly find ourselves in a galaxy that is currently undergoing a violent quasar phase. The very fact that we are here to ponder the question preselects for a cosmic environment that has been stable and benign enough for billions of years to allow for the slow, gradual evolution of intelligence. A quasar outburst is a relatively brief event, but its aftereffects can persist for eons. Our Milky Way's quiet center may therefore be a prerequisite for our existence, a necessary condition written into the cosmic ledger that allowed life to emerge undisturbed. We are the beneficiaries of a long period of galactic peace, a fortunate lull in the storm that has raged since the dawn of galaxies. This perspective forces us to reconsider our place in the cosmos. We are not just inhabitants of a single planet orbiting an average star. We are products of an entire galactic ecosystem that has, for now, settled into a stable and life-friendly equilibrium. The supermassive black holes that power quasars are not merely distant curiosities. They are fundamental regulators of life's potential throughout the universe. Their cycles of activity and quiescence may dictate the rhythm of biological emergence on a galactic scale. As we look out at distant quasars, we are therefore witnessing not just the most powerful engines in the cosmos, but also potential graveyards of worlds where the cosmic struggle between creation and destruction tilted decisively, if temporarily, toward the latter. Our own existence stands as a testament to a rare and precious cosmic calm, a silence in the heart of our galaxy that has allowed our tiny world to buzz with the fragile, beautiful noise of life. And now we reach back to the very beginning, to a time when the universe itself was undergoing a transformation so fundamental that it made the entire cosmos observable. This brings us to one of the most pivotal roles quasars have played in cosmic history, their contribution to the epoch of reionization. To understand this, we have to journey to the cosmic dawn, a period a few 100 million years after the Big Bang. The universe was a very different place then. It was dark but not empty. It was filled with a thick, opaque fog of neutral hydrogen gas. In this primordial state, the hydrogen atoms were complete, each with a single proton and electron bound together. This neutral gas was ravenous for light, particularly the high-energy ultraviolet light that the first stars and galaxies were just beginning to produce. Any ultraviolet photon emitted by these early objects would almost immediately be absorbed by a hydrogen atom, reionizing it for a fleeting moment before it found another electron. The light couldn't travel far. The universe was, for all intents and purposes, a murky swamp, its deepest secrets hidden behind a nearly impenetrable veil. Into this fog, the first quasars ignited. They were the ultimate game changers. While the first populations of stars were certainly pouring ultraviolet light into their immediate surroundings, a single quasar could outshine an entire galaxy of these stars. Its accretion disk acted like a cosmic ultraviolet blowtorch, emitting a ferocious blast of high-energy photons that flooded into the intergalactic medium. The mechanism was direct and violent. When an energetic ultraviolet photon from a quasar collided with a neutral hydrogen atom, it delivered a knockout blow, blasting the electron clean off the proton. The atom was ionized, transformed from a light-absorbing obstacle into a transparent, charged particle, a free proton and a free electron. This process, repeated quadrillions of times over by a single quasar and countless others across the young universe, began to carve out vast, transparent bubbles in the primordial fog. Think of it as a cosmic thaw, where brilliant points of heat began to melt away a global ice age of neutral gas, creating the first clear tunnels through which light could finally travel freely. The sheer power and reach of these early quasars made them uniquely effective at this task. A massive quasar could ionize hydrogen gas far beyond the confines of its own host galaxy, creating an immense transparent region in the intergalactic medium that might span millions of light years. Within these colossal bubbles, the fog had lifted. Light from other, fainter galaxies and stars inside these zones could now travel across the cosmos without being absorbed, their journeys uninterrupted for the first time in cosmic history. As more and more quasars flickered on, and as the first generations of massive stars continued their own ionizing work, these transparent bubbles began to overlap and merge. Over hundreds of millions of years, this process snowballed, a cosmic phase change sweeping across the universe. The once opaque sea of neutral hydrogen was gradually transformed into the transparent, ionized plasma that fills the vast intergalactic spaces today. This was the epoch of reionization, the final major transition of the universe, and quasars were the heavy artillery that helped bring it to a close. The evidence for this monumental event is etched into the light of the most distant quasars we can find. When we point our most powerful telescopes at a quasar from a time before reionization was complete, we see something remarkable in its spectrum, a Gunn-Peterson trough. This is not a forest of individual absorption lines, but a complete and total suppression of any light at wavelengths shorter than the Lyman alpha line, a stark, dark chasm in the spectrum. This trough is the signature of a continuous, unionized medium. It tells us that the space between us and that quasar was still filled with a pervasive fog of neutral hydrogen, which absorbed every single ultraviolet photon the quasar emitted at that specific wavelength. As we look at quasars that are closer, and therefore from a later time, this trough disappears, replaced by the familiar Lyman alpha forest. That forest is itself evidence that reionization has done its work. The neutral hydrogen is no longer a smooth, continuous fog, but has been broken up into discrete, isolated clouds by the ionizing radiation, allowing most of the quasar's light to pass through unimpeded, with only the dense cores of clouds casting their individual shadows. Determining the exact contribution of quasars versus the first stars in this grand process is one of the most active areas of research in cosmology. It's a cosmic detective story of competing influences. The first stars, known as population 3 stars, were likely immensely massive and hot, burning bright and dying young in spectacular supernova. They undoubtedly poured a tremendous amount of ionizing radiation into the early universe. However, their light was often confined to the regions immediately around their host protogalaxies. Quasars, with their sheer, concentrated power, could punch through on much larger scales, creating those enormous ionized bubbles that could interconnect and clear vast volumes of space much more efficiently. The current consensus, bolstered by data from the James Webb Space Telescope, suggests that both were essential players in a complex symphony of ionization. The stars likely began the process, creating the first small, localized clearings in the fog. Then, as the first supermassive black holes grew and ignited into quasars, they provided the powerful, long-range radiation needed to finish the job, ionizing the most stubborn, diffuse regions of gas and ensuring the universe became truly transparent from every vantage point. The success of this reionization was a prerequisite for the universe we see today. Without it, our view of the cosmos would extend only to the nearest stars. The light from every distant galaxy, every quasar, every cosmic event would be absorbed and lost in the primordial haze. Modern astronomy, built on observing the light from the farthest reaches of space and time, would be impossible. The brilliant beacons of the first quasars, therefore, did more than just announce the presence of monstrous black holes. They actively participated in cleaning the cosmic window, forging the clear and transparent universe that allows us to look back over 13 billion years and witness their own glorious, violent birth. Their greatest legacy is the star-filled sky itself, a canvas they helped to unveil, making the cosmos not just a place of immense power, but also a realm of breathtaking visibility. But perhaps the most intellectually profound role that quasars play is as universal laboratories, testing the very laws of physics under conditions of extreme gravity and energy that we could never hope to replicate in any particle collider or experiment on Earth. These distant beacons are not just objects of study, they are active participants in a grand experiment, allowing us to stress test our most fundamental theories to their absolute breaking point. The environment around a supermassive black hole is a place where the curved spacetime of Einstein's general relativity is no longer a subtle correction but the dominant architect of reality, where matter is pushed to energy densities that challenge our understanding of quantum fields, and where the very nature of space and time might reveal secrets hidden from us in our tame, low-energy core. Of the universe, consider first the pure, unadulterated test of general relativity. Einstein's theory has passed every experimental check with flying colors, from the precise orbits of Mercury to the recent detections of gravitational waves. But all these tests have been in what physicists call the weak field limit, where gravity is relatively mild. A quasar's central engine is the ultimate strong field environment. Here, spacetime is not just gently curved, it is twisted into a vortex dragged around by the black hole's furious rotation and ultimately torn apart at the singularity. The accretion disk itself is a battleground where the predictions of relativity become starkly visible. The theory dictates that the inner edge of that disk is defined by the innermost stable circular orbit, a precise boundary inside which no stable orbit is possible, and matter must plunge precipitously toward the event horizon. By carefully studying the light emitted from these inner disks, particularly the broadening of its X-ray emission lines due to the immense gravitational redshift and the Doppler shifts from orbital motion, astronomers can effectively map the spacetime geometry right at the precipice of the black hole. Any deviation from the predictions of general relativity, a subtle shift in the position of that inner edge, or a distortion in the way light is lensed around the black hole, would be a monumental discovery pointing toward a more complete theory of gravity. This probing of spacetime extends to even more subtle and bizarre effects, such as the phenomenon of quasi-periodic oscillations. Observatories like XMM Newton and Chandra have detected rhythmic flickers in the X-ray light from accretion disks around black holes, oscillations that occur at nearly constant frequencies. While the exact mechanism is still debated, one compelling explanation is that these are the heartbeats of the accretion disk itself, related to blobs of hot gas orbiting at the very brink of the innermost stable orbit. In the warped spacetime there, general relativity predicts the existence of peculiar frequencies, an epicyclic frequency related to how quickly a slightly perturbed orbit will oscillate in and out, and the orbital frequency itself. The quasi-periodic oscillations we see are thought to be a direct manifestation of these relativistic frequencies. By measuring them, we are essentially listening to the natural resonant frequencies of spacetime as it is strained to its limit by the black hole's gravity. If these frequencies do not match the precise values predicted by Einstein's equations for a black hole of a given mass and spin, it would be a clear signal that our understanding of strong gravity is incomplete. Beyond refining our existing theories, quasars offer a tantalizing window into physics that lies completely beyond our current standard model. One of the biggest mysteries in cosmology is the nature of dark matter, the invisible substance that makes up most of the matter in the universe. While it doesn't interact with light, it does exert a powerful gravitational pull. Some theoretical physicists have proposed that the dense environments around quasars could be ideal places to look for signs of certain types of dark matter particles. For instance, if dark matter is made of hypothetical particles called actions, the immensely strong magnetic fields near the black hole could convert some of these actions into photons, creating a subtle, specific signature in the quasar's radio emission that we might be able to detect. Other theories suggest that dense cusps of dark matter could accumulate around the black holes, subtly altering the way stars and gas orbit in the galactic center in ways that deviate from the pure predictions of general relativity alone. By using quasars as gravitational anchors, we can search for these minute discrepancies, using the cosmos itself as a particle physics detector on a scale far grander than the Large Hadron Collider. Furthermore, the sheer energetic output of quasars pushes at the boundaries of plasma physics and magnetohydrodynamics, the processes that accelerate particles in their jets to within a fraction of a percent of the speed of light are far more efficient than any process we understand in detail. How is this energy transferred so effectively from the black hole's spin into the jet? How do the magnetic fields remain so coherent over millions of light years? Answering these questions isn't just about understanding quasars. It could revolutionize our own technology. The physics of magnetic reconnection and particle acceleration happening in these jets is the same fundamental physics that governs solar flares, the aurora in our own atmosphere, and even the quest for sustainable fusion energy here on Earth. By studying the most extreme particle accelerators in the universe, we are learning the ultimate limits of how matter and energy behave under the most violent conditions possible, providing a benchmark against which all of our terrestrial physics must be measured. In this light, every flicker of a quasar, every twisted knot in its jet, and every shadow it casts is a piece of data in the greatest experiment ever conceived. They are natural, celestial instruments of unparalleled power, allowing us to conduct precision tests of the laws that govern reality. When we look at a quasar, we are not just seeing a distant, brilliant object. We are witnessing a fundamental probe of the universe's operating system, a place where the known and the unknown collide, and where each new observation has the potential to either firmly cement our current theories or shatter them, forcing us to gaze even deeper into the mystery of what space, time, matter, energy truly are. This entire journey, from the brilliant fury of the central engine to the faint whispers of light echoes, has brought us to the very edge of our current understanding. But the most thrilling chapter in the story of quasars is the one we are just beginning to write, a chapter defined not by what we know, but by what we are on the cusp of discovering. We stand at the precipice of a new golden age of astronomy, powered by a fleet of revolutionary observatories both on the ground and in space, instruments designed to pry open the final secrets of these cosmic behemoths. The future of quasar observations is no longer a distant dream. It is unfolding right now, promising to transform the ghostly blurs in our data into sharp, detailed portraits of the most violent environments in the universe. At the forefront of this charge is the James Webb Space Telescope, an instrument that is fundamentally a time machine tuned to the universe's infancy. While Hubble gave us our first deep views of the early cosmos, Webb's incredible sensitivity in the infrared part of the spectrum is what allows it to peer through the cosmic dust and see the light from the very first galaxies and quasars, light that has been stretched into the infrared by the expansion of the universe over billions of years. Webb isn't just finding quasars a little further back, it is hunting for the primordial ones, the first generation of these monsters to switch on. Its mission is to answer the colossal question of how supermassive black holes could possibly have grown so large so quickly. By analyzing the composition of the gas around these infant quasars, Webb can search for the chemical fingerprints of their formation. Did they grow from the remnants of the first, incredibly massive stars, or were their seeds sown in the direct collapse of pristine gas clouds? a process that would leave a distinct lack of heavy elements in their surroundings. Each new high redshift quasar discovered by Webb is another data point in this cosmic origin story, pushing our view back to an era when the first lights in the universe were just beginning to pierce the primordial darkness. While Webb looks back in time, a new generation of colossal ground-based telescopes is being built to bring the present-day universe into breathtaking focus. The Extremely Large Telescope, or ELT, now under construction in the Chilean Atacama Desert, will be the world's largest eye on the sky when it sees first light later this decade. With a primary mirror a staggering 39 meters across, it will gather more light than all of the largest existing optical telescopes combined. For quasars, this means something extraordinary: the ability to directly study their host galaxies in unprecedented detail, even for objects at tremendous distances. For decades, the host galaxies of the most brilliant quasars have been lost in the blinding glare of their central engines. The ELT, with its revolutionary adaptive optics systems that correct for the blurring of Earth's atmosphere, will be able to peel back that glare as never before. We will see the intricate structures of these galaxies, the tidal tails from past mergers, the swirling spiral arms, the vast populations of stars, allowing us to directly witness the galactic ecosystems that nurture and are shaped by the central black hole. We will be able to watch stars orbiting the central black hole in distant galaxies, providing the most precise measurements yet of the black hole's mass and testing gravity in a regime we have never before been able to access with such clarity. But perhaps the most profound capability of these new instruments lies in their potential for direct imaging. We've discussed the Event Horizon Telescope and its stunning image of the black hole in M87. The next step is to apply this powerful technique of very long, baseline interferometry to active galactic nuclei. The plan is to expand the EHT array by adding new telescopes in strategic locations and even launching space-based radio telescopes to create a virtual observatory with a baseline larger than Earth itself. This ambition, sometimes called the Event Horizon Imager, would provide a resolution so sharp it could make a movie of material orbiting the event horizon of Sagittarius, a star, our own galaxy's supermassive black hole, and eventually target the engines of nearby active galaxies. Imagine watching in real time as blobs of plasma are accelerated down a relativistic jet, or seeing the intricate structure of the magnetic fields at the base of the outflow. This would allow us to directly test the Blandford-Zenagic process and other theories of jet formation, moving from speculative models to direct observation. We could see the shadow of the black hole wobble and change shape as new matter falls in, providing a direct visual test of general relativity in the most extreme gravitational environment imaginable. The data from these telescopes will not operate in isolation. They will form a powerful multi-wavelength symphony. The Vera-C Rubin Observatory, with its relentless all-sky survey, will discover millions of new quasars and, crucially, will catch thousands of them in the act of changing their look, building up a statistical understanding of how often and how quickly these transformations occur. Its rapid-fire observations will provide the triggers for other telescopes to swing into action. When Rubin flags a quasar that has suddenly dimmed or brightened, alerts will be sent to observatories like Swift and Chandra to capture the X-ray response, to the ILT to take a high-resolution spectrum, and to the EHT to see if there are corresponding changes in the inner disk structure. This coordinated, multi-messenger approach will turn these distant points of light into dynamic, three-dimensional laboratories where we can correlate changes in the accretion disk with the response of the broadline region, the launching of jet components, and the expulsion of winds, building a complete and unified picture of how the entire system functions as a single, chaotic engine. The ultimate goal, woven through all these efforts, is to unravel the remaining grand mysteries. How exactly do magnetic fields coupled to the black holes spin to launch jets? What is the true geometry and dynamics of the broad line region and the obscuring torus? Can we finally find unambiguous evidence for the elusive intermediate mass black holes that are the missing link in the growth hierarchy? And most fundamentally, what do quasars tell us about the nature of gravity, space, and time itself? The next generation of observations will provide the data to move from plausible theories to confirmed physical laws. The journey that began with the baffling identification of a star-like object with a bizarre spectrum is now leading us to a future where we will not just infer the properties of these cosmic monsters, but will watch them breathe, flare, and shape the cosmos in real time. The final bizarre phenomenon of quasars is their own enduring mystery, a siren call that continues to pull us deeper into the universe, driving us to build ever greater instruments to satisfy a fundamental human desire to look into the heart of the storm and finally understand the forces that gave birth to the galaxies, the stars, and ultimately to us. From the supermassive black hole engine at their core to the relativistic jets that scream across millions of light years, from their rapid variability that confines unbelievable power into a volume no larger than our solar system to their use as cosmic lighthouses illuminating the expansion of the universe itself, our journey through these 25 phenomena reveals that quasars and active galactic nuclei are far more than just brilliant spectacles. They are the ultimate cosmic crucibles where the laws of physics are pushed to their breaking point. They are the architects of galaxy evolution, whose violent feedback can shut down star formation and sculpt entire galactic ecosystems. They are time machines allowing us to peer back to the universe's infancy and witness the epoch of reionization that made the cosmos transparent. And they are cosmic laboratories, testing everything from general relativity to the nature of dark matter and the origins of the most energetic particles in existence. Each phenomenon, from the Lyman alpha forest and the unified model to the mysterious changing-look quasars and the elusive intermediate mass black holes, intertwines to tell a single, cohesive story: that the evolution of structure in our universe, from the largest galaxy clusters to the potential for life itself, is inextricably linked to the violent, brilliant, and cyclical lives of incredible engines. They are not anomalies, they are fundamental driving forces in the cosmic narrative, and their study has fundamentally reshaped our understanding of reality. Yet, for all we have uncovered, the mysteries are far from solved. We still do not know exactly how the first supermassive black holes grew so big so fast, how magnetic fields so efficiently tap a black hole spin, or what the final, silent whisper of a gravitational wave from a binary merger will ultimately tell us about the fabric of space-time. The universe's most powerful beacons continue to challenge us, inviting the next generation of telescopes and the next great theoretical leaps to unveil their deepest secrets. The story of quasars is still being written, and every new observation adds another line. We want to hear from you which of these bizarre phenomena stretched your mind the most. Was it the sheer power of the black hole engine, the cosmic illusion of gravitational lensing, or the haunting ghost of a light echo? Share your thoughts in the comments below, and if you enjoyed this deep dive into the heart of cosmic mysteries, make sure to subscribe and hit the notification bell so you don't miss our next journey